share screen?
I think it would be a good idea, please.
Okay. I think, no, I need some permission, I think.
Yeah, I will. I have to make you. Okay, Organ. Okay, Ashoke, now you should be able to share your screen.
Yeah. The screen visible?
Yes, we can see it.
Okay.
Could you make it full screen?
Yeah.
Yes.
Perfect.
This is okay?
Looks great. Yeah.
Change the slide, okay.
So Ashok, it is already 3 minutes past the hour, so I presume it's okay we start now then?
Okay.
Okay, so well, welcome to the second day of this conference, where the first speaker is Ashoke Sen, who will speak about gravitational waves and soft theorems. So please share your screen again.
Okay, thank you very much. Okay, so first of all, I'd like to thank the organizers for inviting me to speak in this conference. So today I'm going to give a general overview of the results of last few years on the developments that relate classical gravitational radiation to soft theorems. So here is the plan. So the first part of the talk will be to summarize the results. Okay, and in fact, this will be about half of the talk. And here you will see that there are new results as well as old results. Okay, but there will be also new viewpoint for older results, like memory effect. And then I'll focus on the new results, which you can call the tail to the memory. Then I'll give a classical derivation of these results. And then finally, I'll discuss its relation to soft theorems. Okay, and then I'll conclude with some few comments. So let me then begin by giving the general results, what the kind of results that we have and how we get them. So for this, let's consider a classical scattering in space. And the classical scattering means a set of objects with asymptotic 4 momenta which are leveled by the primes p1 prime to pm prime. So they come together, they interact via complicated forces, and then they again disperse as a set of other objects with asymptotic 4 momenta which I'll call p1 to pn. So you can see the number of particles can change. The particles can exchange momentum, energy, masses, various quantum numbers, etc. And here is the relationship between the momenta and the masses, the standard mass cell condition. So our goal will be to discuss the scattering process. So we'll choose the origin of space-time to be somewhere in the region where the scattering event takes place. Okay, the precise choice will not be important. And our interest will be in a detector T that is placed at Scribe plus, which you can think of as a faraway point X, and it detects the gravitational wave, gravitational radiation, which is the difference between the metric and the Minkowski metric. And let's suppose that the gravitational wave reaches the detector around some time t0. So t0 will be given by the light travel time, and then there are corrections, logarithmic corrections, which come due to the gravitational drag on the gravitational radiation. Again, for the time being, we'll not really worry too much about these corrections. And so t0 somewhere is roughly the time at which the peak of the gravitational wave reaches the faraway detector. So we'll define retarded time at the detector, u, which is the t minus t0. Again, u is not precisely defined because t0 is not precisely defined, but again, that will not really make a difference. And our focus will be on the late and early time tail of the radiation, which means that we will focus on the value of h mu nu at the detector at large positive u and large negative u. Now, it turns out that instead of working with h mu nu, it's easier to work with the trace reverse version of h mu nu. So e mu nu, which is defined here. Now, by working with E mu nu, you don't lose anything because you can reconstruct H mu nu from E mu nu by the reverse relation. Okay, so it's just the formula look a little simpler in terms of E mu nu. And what we find is that up to gauge transformations and corrections of order r to the minus 2, E mu nu is given by a form like this. So at far future, at large positive U, it has a constant piece. Then it has a piece proportional to 1 over U. And then the corrections of order u to the minus u to the minus 2 log u. And for large negative U, it has a correction of this kind. And here I should just add that I have by convention chosen E mu to vanish in the far past, because I'll assume that the metric is exactly Minkowski eta mu nu in the far past. Okay, so there's a constant piece here. And the main point that I want to emphasize here is that these coefficients A mu nu, B mu nu, and C mu nu, these are given solely by the momenta of the ingoing and outgoing objects without requiring any knowledge of the details of the scattering process. So in the next slide, I'll give the expressions for these quantities. The expressions themselves are somewhat complicated, but the main point I want to emphasize in those expressions is that it depends only on the momenta of the ingoing and outgoing objects. So here is the expression for A mu nu, B mu nu, and C mu nu. I have not set anything equal to 1, so the Newton's constant, the speed of light, everything is in this formula. So you can see that most of these I have already introduced before. Okay, n I have not introduced before. So n is a 4 vector whose 0th component by definition is 1, and whose spatial components is the direction cosine of the detector with respect to the place where the scattering took place. Okay, so x over r. And you can see that everything else depends only on these quantities. Okay, so as long as you know the incoming and outgoing momenta, okay, and you fix a direction in which you have placed the detector, you know precisely what this A mu nu, B mu nu, and C mu nu are. So let me go back to these expressions again. So A mu nu is what is normally known as the memory term. And what this represents physically is a permanent change in the state of the detector after the gravitational wave has passed. Okay? Because you can see that if you start with the metric eta mu nu to begin with, after the gravitational wave has passed, it becomes eta mu nu plus a constant. Okay, the constant depends. So you have from E mu nu, you have to reconstruct H mu nu, and that fixes the final metric. And this, of course, the memory effect was discovered long time ago in the 70s. Okay. But recent work by Strominger and others showed that this is related to what we call the leading soft graviton theorem. These coefficients, B mu nu and C mu nu, are what we can call tail terms because they are subleading in the large U limit. And these are related to logarithmic terms in the subleading soft graviton theorem. Okay, and we will see some of these later in the talk. So here I want to make some comments on this result. Okay, the first point that I want to emphasize is that the result that I have quoted is a statement in classical general relativity. There is no h bar in the formula, even though it was originally suggested by quantum soft graviton theorem. And I'll give the logic that led to this formula, but it's really a statement in classical GR. And indeed, now we have a fully classical derivation, and I'll describe that derivation later in this talk. This I have already emphasized that these coefficients can be expressed in terms of the momenta of the incoming and outgoing objects without knowing what forces operated or how the objects move during the scattering. So it requires no knowledge about the scattering process. It doesn't have to be purely gravitational. There can be complicated strong interaction, electromagnetic weak interaction during this scattering. But nothing affects the result as long as you know the final state momentum, final and initial state momentum. Again, this is a consequence of soft graviton theorem. This result one can show matches explicit known results in spatial cases. Okay, some of these results are very old, like the result of Peters okay, where he calculated the radiation from a particle moving in Schwarzschild background. And then there are some more recent results, okay, and they all follow, at least in appropriate limits, they reproduce the results that we have quoted. Now, if you have charged particles in the initial and the final state, then there are known corrections to this formula that I showed due to long-range electromagnetic interactions. So these can be easily accounted for, but the formula will look more complicated, and that's why I have not written them down explicitly. Now, in the expressions for A mu nu and B mu nu, the sum over final state particles Ij that we have, let me go back and show the expressions again. So you see the unprimed ones are the final state momenta, the primed ones are the initial state momenta. And so you can see that the expressions for A mu nu and B mu nu actually contains some sum over final state particles. And this sum includes any gravitational radiation that is emitted during this process. So this is sum over all particles. So this is what I have said here, that here the sum over final states includes integration over outgoing flux of radiation. And the way we include the effect of that is to regard this as a flux of massless particles. And again, for A mu nu, this effect has been known for quite some time. This is known as the nonlinear memory term. And this is in fact indeed present. Now it turns out that due to some miraculous cancellation, in the expression for B mu nu, which also a priori depends on the final state massless particle momenta, the contribution from massless final states can actually be re-expressed in terms of the massive state momenta. And here is a simple rule. So I should emphasize that this rule is not a new rule. Okay, you can just start from this expression over here, okay, that we see here, and simply set some of the particle masses to 0 and see, analyze that contribution. And here is what we find. So the simple rule that one arrives at is that we simply drop sum over all final state massless particles or radiation, and then add a correction, which is given here. So here PF is the total outgoing momentum carried by massive particles in the final state, and Pi is the total incoming momentum. So if there are no final state massless particles, then of course Pi and PF are the same by momentum conservation, and this vanishes identically. But if there are final state massless particles, then you have to add this correction. And this makes life very simple for computing B mu nu, because this says that we don't really have to calculate the final state gravitational radiation to figure out the late time behavior of the gravitational waveform. Because all we need is the final state massive particle momentum. Now the special case of this is explosion, okay, where you have one particle in the initial state and it just splits apart into multiple particles. And this includes in particular the binary black hole merger problem, because the initial state you can think of as a single bound object. And the final state, of course, contains a black hole plus a gravitational radiation. So this includes both binary black holes as well as black hole neutron star or neutron star neutron star. Okay, as long as the initial object is bound, you can just think of this as a one object. So the same formula works, except that in the initial state, we just put one object. In this case, C mu nu vanishes. There is no initial state radiation. And E mu nu at late time, okay, has this form, A and B. And because of the same cancellation that we mentioned earlier, okay, the fact that B mu nu can be expressed in terms of the final state massive particles only, it turns out that B mu nu vanishes unless there are at least two massive objects in the final state. So this vanishing is somewhat surprising, because when one actually does the computation explicitly, one finds that it's a result of cancellation between two apparently different effects. One effect is a soft radiation from the final state objects, because they accelerate under each other's gravitational field. And the other effect is the backscattering of the leading order soft radiation, that's the memory, in the gravitational field of the outgoing matter and radiation. And these two effects cancel and makes B mu nu vanish in the final state unless there are more than one massive object. And as I said, this means in particular that B mu nu will vanish for binary black hole merger. Okay, because in this case, the final state has only one massive object, that's one black hole. On the other hand, if you have a black hole neutron star merger, for example, okay, where some matter gets ejected, then B mu nu may receive some corrections, some contribution. Now, it turns out that we can also extend this result to next order, to order u to the minus 2 log u. These results again were conjectured first using soft theorem, and then they are proved by classical analysis. So these formulae obviously look more complicated than what we had earlier, but again, what I want to emphasize is not the specific form of the formulae, but the fact that they depend exactly on the same data, okay? The initial and the final momenta and the direction of the detector, and the direction along which the detector is placed. So here I have given the formulae. So this is the correction to E mu nu to next order, okay? U to the minus 2 log u corrections. This coefficient F mu nu is given here. We can see that this depends both on the final momenta, that's the unprimed momenta, and the initial momenta, that's the prime momenta. And in the forward past, we have this G mu nu, which is given here. This depends only on the incoming momenta. So these are the formulae for F and G. And you can see that they depend on the same data in the sense that they depend on the initial and final momenta, and this vector n that we had introduced earlier, whose first component, whose zeroth component is 1, and the spatial component is just the direction for the unit vector along the direction of the detector. It turns out that the same miraculous cancellation continues, that in the sum over final states, to begin with, we should include massless state contribution. But again, one finds that we can drop the contribution from massless states at the cost of adding a correction term that depends only on the massive state momentum. So even for computing F mu, you don't need any data on final state gravitational radiation, except the total energy and momentum that it carries away. Okay? And that is, of course, is encoded in the momenta of the final state massive particles. Okay? So here is the formula. So Pi is the total initial state momenta. Pf is the total final state momentum, but only carried by massive particles. And this P tilde I label momenta of the massive final state particles. So in this sum, for example, what we add, these corrections, the sum includes only over massive final states. And as before, if Pi is equal to Pf, then of course the correction vanishes, okay, because then you have the whole answer anyway. And again, if you have an explosion, then F mu nu will vanish unless there are at least two massive objects in the final state. And this includes the case of binary black hole merger. Okay, so for binary black hole merger, even the u to the minus 2 log u term vanishes. Now, you would notice that so far in our formulae, there is no spin dependence. Okay, nothing depends on the spins of the incoming and outgoing objects. Okay. So this is not because we have not taken into account the effect of spin. Okay, our analysis includes the effect of spin, okay, except that to the order that you have presented the results, the spin dependence just drops out. Okay. From soft theorem, one expects that the spin dependence will come at order u to the minus 2. But at this order, there are also non-universal terms. And these non-universal terms basically come from the fact that if you look at u to the minus 2 log u, okay, log u, of course, has an additive ambiguity because it's u over something, and that's some kind of cutoff. And we'll see that cutoff is provided by the size of the scattering region. Okay. So u to the minus 2 term is ambiguous, but that is proportional to g cube. So it turns out that if you are to order g square over u square, then one can get an unambiguous expression for the spin dependent terms. And this is still to appear by these authors over here. So we can include spin dependence also in our analysis. So this is more or less the end of the review of the results. And now I'll try to go through the derivation, the classical derivation first, then the logic that we use for getting the result from soft theorem. So let me begin with the classical derivation. So the way we analyze this problem is that we divide the space-time into the scattering region. We'll call this region scattering region. Some region that contains the place where the scattering took place. So all the complicated interactions we'll assume is taking place inside the scattering region. That could be, this could involve strong nuclear force for all you know. And then the asymptotic region, F, where the particles interact via long-range gravitational force. And if the particles are charged, as I have already indicated, there'll also be long-range electromagnetic force. But in the analysis that I'm going to describe, I'll just ignore it. But that effect can easily be taken into account. And so the idea is that we iteratively solve the coupled equations of motion of matter and gravity in the asymptotic region. And the way we do it is that, so typically, if you want to regard this as an initial value problem, then we start with some matter, some incoming objects, and then we evolve the system forward by equations of motion. But of course, in that case, once it enters the scattering region, where there will be strong interactions, we cannot evolve the system without knowing what happens in the scattering region. But the way we proceed is to evolve the matter equations forward in time for the incoming particles, because here you know the initial data, and backward for the outgoing particles, because we are assuming that we know the final state momenta. So given the knowledge of the final state momenta, we can evolve the equations for the matter backward in time. For gravitational equations, of course, we always use evolve them forward in time using retarded Green's function. So this is the general principle that we will be using in deriving the results that I quoted. And the main difference from the usual approach to studying problems of this kind is the fact that we are providing partly initial state data, but also partly final state data. So we don't want to get the final state starting from the initial state data, because that will certainly require knowing what happened inside this region S. So here is some more detail of what we do. So we'll split the metric into the flat part and then the fluctuation to h mu nu. But we are not assuming gravity to be weak at this stage. H mu nu can be large. And then we define E mu nu as a trace reverse version of H mu nu. And after we do that, we raise and lower indices by the flat metric eta. Once we have defined E mu nu this way, any further raising and lowering of indices will be done with flat metric. So now we try to rewrite Einstein's equation in the de Dondert gauge in this form. So this box here is the standard flat space Laplacian. All the complication of nonlinear gravity has gone into T mu nu, because T mu nu here is the matter contribution, which I'll denote by Tx mu nu, and then the contribution from the gravitational energy momentum tensor. So this essentially captures all terms that are quadratic and higher order in H mu nu on the left hand side of Einstein's equation. So this equation is a formal way of writing Einstein's equation, where you have kept everything other than the linear term on the right hand side, and dump that into the gravitational energy momentum tensor. So this one I have already said that indices will be raised and lowered by flat metric, and you are not assuming weak gravity at this stage. So H mu nu can be large, and certainly inside the scattering region, it is in general large. Okay, so you have this equation over here. So formally, this can be solved by retarded Green's function. Now, of course, it's not really a solution because T mu nu on this side involves E mu nu. What it allows us to do, okay, is to set up an iterative scheme to find E mu nu. Okay, but this is just a formal expression that I've written at this stage. Now, GR, of course, is explicitly known because this is the flat space retarded Green's function. So using the form of GR, one can show that for large R, okay, which is mod x, okay, if you take the Fourier transform of E mu nu in the time variable, okay, you give the space variable as it is and take a Fourier transform of the time variable, we call it E tilde mu nu, omega and x, okay, that's defined here. Then this can be related to the full Fourier transform of energy momentum tensor. So T hat here is the full Fourier transform of energy momentum tensor. Okay. And there is a simple relation between E tilde and T hat. Okay. Omega is basically this Fourier transform variable that appears here. Okay. And the vector k that appears here, or the 4 vector k, okay, its 0th component is omega, okay, which is it shares with E or E tilde. And the spatial components are omega times n hat, where n hat is essentially the direction cosine of the unit vector along the direction of the detector, okay, x. So this will be making use of. Okay. And T hat mu nu, again, let me remind you that gets contribution both from matter as well as gravitational energy momentum tensor. Okay. So in general, this is a highly complicated function of H mu. Okay. So this is not a solution, but just some relation between E tilde and T hat. Now, what one can show by examining simple properties of Fourier transform, that the memory term, okay, which is the constant piece, the jump in E mu nu, okay, and then the U inverse term and the U to the minus 2 log U term in the expression for E mu nu, they arise from terms of order 1 over omega, okay, log omega, and omega log omega square term in T hat mu nu. Okay, that's what we find by Fourier transform. Okay. Now, you would notice that each of these terms, okay, is non-analytic function of omega, okay, which means that if you take sufficient number of derivatives with respect to omega, it should blow up at omega equal to 0. And that is going to be important for what we are going to describe next. So here is the expression for E tilde mu nu and T hat, the same relation that we wrote down. Now this integral, okay, over the whole space time. But now we are going to divide this integral into two parts, two regions. Okay, one is the scattering region, okay, where all the strong interaction takes place, okay, and the other one is the asymptotic region F, which is the complement of S, and here only long-range gravitational forces are relevant. So the complicated contribution to T hat mu nu, of course, is in the scattering region. Okay. But the scattering region, okay, is a finite region in space-time. Okay. And because our goal is to calculate the non-analytic part of T hat mu nu, that means if you differentiate T hat sufficient number of times with respect to omega, you should get divergent result, okay, at omega equal to 0. So for those kinds of terms, it's clear that if you integrate over a finite region of space-time, they cannot give divergent contribution as omega goes to 0, however number of derivatives you take here. So this argument can be used to say that the terms that you are looking for, okay, in T hat mu nu must come from integration over the asymptotic region. And the asymptotic region, of course, is easy to handle because there we can regard the matter energy momentum tensor as the two incoming and outgoing object trajectories. And the gravitational energy momentum tensor, you can use the standard formula for gravitational energy momentum tensor. And because far away from the scattering region, the gravitational field is weak, okay, here it makes sense to expand in powers of H mu. Okay, and that's the procedure that will be following. So in this slide, I have written a list of all the formulae that we need. So this is the energy momentum tensor of the matter. Okay, so we think of the incoming and outgoing matter as point particles, Okay. Now, of course, there are corrections to this. Okay, there are, for example, the leading correction to this is spin dependent, okay, which involves derivatives of the delta function, and then there are further non-universal corrections. But one can show that all of those corrections, okay, do not contribute to the order that we are interested in. Then you have the total energy momentum tensor, the sum of Tx and Th. Okay, this is the gravitational energy momentum tensor. I have not written it down because it's complicated, but there's a well-defined expression for Th. Then we have this equation, which you already wrote down. And here are the equations that describe the point particle trajectories. Okay. Now, this is what you normally do in studying gravitational radiation from point particle dynamics. Okay. What is special about the kind of way we are going to do the analysis, okay, is a boundary condition. Okay, and this I have already alluded to before. The boundary condition that we'll be using, okay, is that xi, of course, we'll put at tau equal to 0. Okay, tau equal to 0 is basically the region where the point where it emerges from the scattering region. Okay, tau is the proper time of the trajectory, along the trajectory. Okay. But here you see that we put the boundary condition on the dx dt, okay, on the momentum, in the far future for the outgoing particle trajectories, and in the far past for the incoming particle trajectories. And that's because we are assuming that we know the data of the momentum in the far future and momentum in the far past. And that's the main difference from the usual approach to studying gravitational radiation from scattering processes like this. Okay, that we provide data in the final state as well as in the initial state. So you basically solve it.
Can I just interrupt? I just want to tell you that you've been speaking for 30 minutes.
30 minutes, okay. Thank you. Okay. Okay, so you solve these equations iteratively. Okay, we have these equations, so you solve these iteratively. Okay. So the starting solution is here. Okay, we take E mu to be 0, x mu to be just free particle trajectory, so Ci mu plus Vi mu tau, and x prime mu, again, free particle trajectory, which is given here. Okay. So once we start with this, we now plug it back in these equations. Okay. So in particular, you calculate E now from this, because T is now only Tx, so you calculate E. Then using that E, you calculate Th, okay, that determines the correction to T mu nu. Okay. Using the same E, we calculate the corrections to the trajectories. Okay. That gives the corrected trajectory, okay, and then put it back and iterate again. Okay. So that's the iterative procedure. Okay. And this iterative procedure generates a series expansion in Gm times omega, okay, but possibly with corrections involving log omega factors. And these log omega factors are in fact relevant ones for getting these 1 over u and 1 over u square log u terms. Now it turns out that if you are interested in getting the omega inverse and the log omega terms, okay, log omega terms give you the 1 over u corrections, then it's enough to do just one iteration. Okay, you start with the free particle dynamics, then do one iteration, okay, and you get the result to the desired order. If you want the result to omega for omega square log omega term, okay, that's needed. If you want the 1 over u square log u term, sorry, this should be omega log omega square. I'm sorry, omega and then square of log omega. Okay, not omega square log omega. That's the next subleading term. Then we need one more iteration. Okay. And these, in practical terms, these are very similar to computing loop diagrams in quantum field theory, except that we have to use retarded propagators, and the propagator for the matter fields is basically the iconal propagator. Otherwise, it's like calculating loop amplitudes in quantum field theories. Anyway, so this is the procedure, and at the end, by taking the Fourier transform, we recover the results that we quoted earlier. Okay, so now let me briefly discuss the relation to soft theorem. Okay, the logic that you use to go from soft theorem to this result. So soft theorems give the result for an amplitude with m soft gravitons in terms of the amplitude without soft gravitons. Okay, this is the main content of soft theorem. And this is simplest to state in dimension larger than 5, because here the S matrix is free from our intra divergence, and it's clear what you are relating, right? You are relating two finite quantities. One is the amplitude without soft low energy gravitons, and the one with amplitude with low energy gravitons. And the general structure of soft theorem is that the amplitude, the scattering matrix of a soft particle plus hard particle, is given by some operator acting on the scattering amplitude for hard particles only. So this is an operator, okay, a matrix differential operator, and this involves the orbital angular momentum and the spin angular momentum of external states. So because it involves spin angular momentum, it acts as a matrix. Because it involves orbital angular momentum, okay, which is p times x minus x times p. Okay, so x you write as a derivative with respect to p, so it becomes a differential operator. Okay, that's the reason why it's a matrix differential operator. But the classical limit is taken by taking the hard particles to be heavy. Okay, so we'll assume that all the hard particles have mass larger than m Planck. Okay. And then we also replace the orbital and angular momentum operators by classical spin and classical orbital angular momentum of external states. Okay, so that's the way we go to the classical limit of these relations. So in this limit, it turns out that the soft theorem simplifies, okay, and the relation takes a form like this. It becomes a factorized form. Okay. So here S alpha, okay, depends only on the quantum number of the alpha soft particle and of course the quantum numbers of the hard particles. It depends on the angular momentum or both orbital and spin angular momentum of the hard particles. Okay. But it depends only on the quantum numbers of the alpha soft particle. Okay, so it factorizes. Different soft particles don't talk to each other. So given this, we can now ask, okay, how to calculate the conditional probability of emitting m soft gravitons of certain quantum number, that means more or less m identical soft gravitons, okay, for given set of classical hard incoming and outgoing particles. Okay, imagine that the hard particle incoming and outgoing momenta are fixed, and you want to calculate the conditional. So that's the given thing. And then you have calculate the conditional probability for emitting m soft gravitons. So that's of course given by squaring this amplitude, okay, and then doing a phase space integral for each of these soft gravitons. And that's what I've written here. So it's 1 over m factorial is the symmetry factor because you have m identical particles in the final state. Then you have mod s to the 2m, okay, because there are m identical s's. Okay. Then you have the phase space factor to the power m, and then a hard mod square. And in the final result, this A hard plays no role. And the idea is that by maximizing this with respect to M, we can find the classical number of soft gravitons with given quantum numbers. And this can be used to determine the Fourier transform of the gravitational waveform up to a phase. Okay, because once we know the number of classical soft gravitons, we can calculate the gravitational waveform, okay, up to a phase. So for d larger than 5, okay, this formula has been tested in many examples. Okay, and indeed, the soft factor gives the gravitational waveform without any additional phase. But in d equal to 4, there are some turn out to be two subtleties. Okay. The first subtlety, as I have already said, S alpha depends on the angular momentum of the hard particles. Okay. But because of the long-range gravitational force of the other particles, this x mu has logarithmic correction to its trajectory. So when you look at the hard particle trajectory, the final and initial state hard particle trajectory, you find that there are corrections of this kind. So this, of course, drops out in this antisymmetrized product, but there are logarithmic corrections, okay, which give a logarithmic correction to J mu. Okay. And that means that Gi mu nu is not well defined as tau goes to infinity, it diverges. Okay. And that makes the soft factor divergent. So what we do is that we basically use the wavelength of the gravitational wave as an ad hoc infrared cutoff on tau. Okay, that's the way we deal with this in 4 dimensions. The second subtlety comes because of the fact that there is long-range gravitational force on the soft gravitons, okay, and this introduces a Coulomb phase. Okay. So in particular, the normal e to the I omega r that we see in particle scattering is replaced by e to the I omega times r minus c log r with some known coefficient c. Okay. And this is basically the result of the gravitational drag on the soft radiation. Now here, of course, log r, okay, we have to ask what log of r times of what. Okay, this should be a dimensionless quantity. Okay. And here again, we make an ad hoc consensus that we should replace r log r by log r omega. Okay. And the intuition here is that the Coulomb drag on the wave of wavelength lambda acts over a distance lambda to r. And that means that log r should really be log r over lambda. Okay, that's the same as log r times omega. And it turns out that if you make these two replacements, two ways of regularization, the two infrared regularization, then it correctly captures the effect of gravitational backscattering. And this reproduces the result that he quoted earlier. So you see from here that in d equal to 4, the classical results from soft theorem should really be regarded as conjectures rather than derivations. Because we had to make this ad hoc assumption about the cutoffs. Nevertheless, soft theorems do lead to correct conjectures. But more importantly, what it teaches us is what questions might have universal answers. And that's independent of the details of the scattering. And in particular, it told us that to get universal answers, we have to specify both the momenta of the initial and the final state hard particles, instead of just giving the initial data. If you are just given the initial data, then we don't expect universal answers, because then the final result will depend on the details of the scattering process. But if you give the data for initial as well as the final state momenta, then you can expect universal answers. Okay, so this is more or less the end of the talk, but let me just say a few words about relation to Price's theorem. Now, this is a slide I have added, because this was a question that was raised in an earlier talk of at Potsdam by both Thibault Damour and Luc Blanchet. So, and the question was, what is the relation to Price's theorem? So let me say a few words about what is Price's theorem. So in the original form, Price's theorem is a statement on late time fall off of gravitational field fluctuation around a black hole of fixed radial distance. Okay, so you take a black hole, take a point at fixed radial distance, and Price's theorem tells us how the gravitational fluctuation should fall off with time. Now, what we are looking for here is the fall off at Scri plus. Now, these authors discussed possible extension of this theorem to Scri plus, okay, but only for massless scalars. And they all really analyzed it using linear perturbation and numerical techniques. So there are some results, but there are also really concrete understanding of what this gives. And as far as I know, there is really no result for h mu nu, okay, at Scri plus at late and early time. So at least our results do not seem to follow from any known version of Price's theorem at Scri plus. But what we can do is to turn this around and regard our result at large U as a precise version of Price's theorem at Scri plus. Because we have a precise result for how the gravitational field falls off at large U in terms of the initial and the final data. And that we can think of as a precise statement of Price's theorem. Okay, so here is for the future. So what we saw is the parallel decay in U comes from non-analytic function in frequency space. So these arise from infrared divergent terms and should therefore be determined by soft physics. So given this, we can ask these questions. First of all, can we develop a systematic procedure for computing all higher order terms in large U expansion? That means we are asking for anything that happens after the quasi-normal mode subdive, right, which drive exponentially. After that, we should be able to get everything from soft physics. Then you can ask, does the magical independence of the result on the final state massless particle data continue to hold, okay, in this expansion? And do all such terms vanish for the black hole merger problem? So with these questions, I'll stop. Thank you.
Thanks very much, Ashok. We have still time for some questions. Please raise your hand. Maybe I begin with a naive question, maybe, but you mentioned that if you add other interactions with long range, your results would require some modifications. Does that include also modification of this kind of theorem you have, that you can rewrite everything in terms of just the massive momenta, incoming and outgoing?
Yeah, I think as long as you're considering gravitational radiation, it turns out to be the case. At least we have checked it for the 1 over U case, 1 over U term, right? 1 over U square log U, I have not checked explicitly. but I feel that it probably works that way, the same way there also. Okay, but that has not been checked for the 1 over U square log U.
And would you have a kind of intuitive explanation for why it has this behavior?
Yeah, I don't know really. I mean, it was quite a surprise to us. And yeah, there must be something in, I mean, some property of gravitational field equations which does this, right? But what it is, we don't know.
So it seems it would be nice to derive it in a way, because you rewrite it in this form, right? But it seems that it's more natural actually to express it immediately in that form you give.
Exactly. Yeah. Because I mean, computing gravitational radiation, of course, is very complicated, right? Final state gravitational radiation. This is a much nicer form, right? Given in terms of just the data of massive particles.
Exactly. Yeah. Other questions? Comments? No, doesn't seem to be so. Well, thanks a lot for zooming in from India, I guess, Ashok.
Thank you very much.
Thanks again. And then we move on.
Wait a second. Wait a second. There is Andy Strominger that is trying. This is waving his hands.
Now I see the waving.
Gabriele is trying
Andy has a question. Indeed, there are 3 questions. Very good.
And also Barack Hall. There are many actually.
They were not visible on my screen. Now I see them.
Okay.
Very good. Thanks.
So go ahead, please.
Two questions. One is, can you understand this as somehow related to the Ward identity of some kind of asymptotic symmetry and this log, this extra phenomena? And secondly, is there, I've just been, I mean, this is beautiful work. I've been very puzzled why it's only there for massive particles. Is there a conceptual explanation for that?
For this one?
Yeah, so 2 questions. Yeah, different questions, yeah.
Yeah, so this one, we have no idea, I mean, why it happens. But, I mean, that's why it's really a surprise that it did happen. The other question you're asking about getting this from BMS kind of symmetry, is that?
Yeah.
This cancellation or the result itself?
Well, the logarithmic correction is an identity among different. Ultimately, comes from an identity. Logarithmic correction of the soft theorem ultimately is an identity among S matrix elements, and any relationship among S matrix elements should somehow be understood as a symmetry. The question is whether you can write it in a nice form.
Yeah,
I think you couldn't.
Yeah, I mean, the only paper I know is by Ladda and Campaglia. They have given a way to understand it from BMS, okay? The corrections to BMS symmetry or asymptotic symmetry. I don't know if Alok is on, maybe he can reply, or any of them. Yeah, so that's
a correction to the leading symmetry, not a new symmetry in and of itself.
That's right, yeah.
Because it only happens when the other one also happens. It never happens on its own.
That's right, yeah.
You couldn't arrange to have this tail without also having a shift?
I think you could. You could imagine a situation where A mu nu is 0, but B mu nu is not 0. Yeah, you could arrange in principle. Because the A mu nu depends on the final state massless radiation, right? So you could adjust the final state massless radiation to cancel A mu nu, and B mu nu will still survive.
Okay, I'm sorry I missed the raised hands. Can we move on to maybe the last question of Barak Cole? Please unmute yourself, Barak.
Okay, Mike. So now we are right leg up, left leg back.
Oh, okay. Can you hear me now?
Yes.
Oh, great. So hi, Ashok, and thank you for the talk. And I have an elementary question about the physical content of these quantities A, B, and C. How would one measure A, B, and C? And how realistic is it to measure them in the future?
Yeah, so to measure it, you basically use the same kind of experiment that you will do for memory effect, right? The overall shift. But here you will find that you approach the final detector position with a 1/u correction. That's the way to measure A, B, and C. And the order of magnitude of these is more or less the same as the memory effect, right? So in principle, if you can see the memory effect, you should also be able to see this, okay? Or the absence of this, because in the binary black hole merger problem, for example, there is memory effect, okay? But this effect is absent because of cancellation between two terms. But any one of those terms would be of the same order as a memory effect. But in supernova explosion, for example, okay, this will be very much there. And if you could see the memory effect there, you will also see this as a 1/u correction to the final detector position.
All right, thank you very much. I think we have to cut it here, unfortunately. Thanks again, Ashoke.
Thank you very much.
And we move on to Luc Blanchet. Is Luc here?
Yes, I am here.
Hi.
So should I share my screen?
Please.
So.
And again, I will warn you after 30 minutes, so you have an idea of where you are.
Okay.
So please, could you make it full screen?
Can you see it?
Yes, but could you make it full screen?
In principle, I have done it.
It's good. Very good. So please go ahead. Your title is on the screen. Yeah.
Do you see my mouse?
Also, yes.
Okay, very good. So thank you very much for the invitation. We discuss today what I will call the traditional post-Newtonian approach to describe the dynamics and gravitational wave emission from compact binary systems in the inspiral phase before the final merger of these systems. And in this talk, I will try to contrast the post-Newtonian approximation, excuse me. I will try to contrast the post-Newtonian approximation to the approach which is very much followed these days, which is based on the effective field theory. So let me just remind the famous gravitational chirp of binary black hole, which consists of some inspiraling phase during which the evolution of the amplitude and the frequency is adiabatic, and the adiabatic parameter in this evolution is directly a small post-Newtonian quantity. So the post-Newtonian approximation is the right approximation to use during this inspiral phase. And then it will break close to the merger, and the merger itself and the ring down will be computed by numerical relativity. For real data analysis in LIGO, Virgo, Cagra detectors, and probably later in space LISA, in the case of black holes, we need also very sophisticated inspiral merger ring-down models that are able to interpolate between the initial inspiral phase described by post-Newtonian theory and the final merger computed numerically. And there are essentially two classes of such models. One is the effective one-body approach, which was described by Alessandra and Thibault yesterday. And the other one is, the properly speaking, inspiral merger ring-down model, which starts from the post-Newtonian waveform in the inspiral phase and completes it by an intermediate phase described phenomenologically by means of some parameters, as well as the merger ring-down phase, which is also described by further parameters. And so these methods are crucial in the data analysis in the case of black hole mergers, collisions. In the case of neutron-star mergers, actually the detectors are sensitive essentially during to the inspiral phase before the merger, and the PN approximation is essentially sufficient for detection and parameter estimation. So traditionally, we describe the method to compute gravitational wave templates in this figure, where in the horizontal axis we have the slow motion parameter of post-Newtonian theory, V over C, which, because of the virial theorem for bond system, is also given by the compacity parameter of your system, Gm over R. And in the vertical axis, we plot the mass ratio between the two objects, or actually the symmetric mass ratio between the two objects. So post-Newtonian theory is valid for any masses, but provided that the slow motion parameter is small with respect to 1. So this means that the two objects are far apart, and the orbit is non-relativistic in this sense. Also, the computations involve many relativistic high-order corrections. And on the other hand, if the two objects are close to each other, the gravity is strong, post-Newtonian theory cannot be applied, but you can do your computations in the case where the symmetric mass ratio is very small, in which case you can use black hole perturbation theory. If you are in the strong field regime and you have masses that are comparable, then you have a numerical integration of your field equation to produce the waveform. There is a very important and nice overlap between perturbation theory, black hole perturbation theory, and the post-Newtonian approximation, in the case where you have a system which obviously will have a very small mass ratio, so that your perturbation theory can be applied, and on the other hand, for which the motion, the orbital motion, is slow with respect to the speed of light. In this case, you will use the gravitational self-force theory, which computes the deviation of the small black hole in the field of the big black hole by means of the deviation with respect to the geodesics of the background geometry associated with the big black hole. And the deviation is the self-force, is called the self-force, which obviously is proportional to the mass ratio between the two objects. And the predictions between post-Newtonian theory are very much consistent with the prediction from perturbation theory, either analytical prediction for gravitational self-force or even numerical predictions modulo some fit to the numerical prediction. And so the situation is very nice. This overlap has been very nicely described by both approximations. On the other hand, we hear very much in this workshop about the post-Minkowskian expansion. So now I plot the post-Minkowskian expansion and the PN expansion in this figure, where I still have the slow motion parameter in the horizontal axis, but I plot directly the compacity parameter of your system, M over R, on the vertical axis. So my post-Newtonian theory is still there, where the slow motion parameter is small, and my post-Minkowskian approximation is located in this region where the compacity parameter is small, and therefore the field generated by my system is weak. In this plot, I don't restrict the two systems that are bound. So there can be a scattering of two black holes, starting from quasi-hyperbolic orbits, and then deviate, and there will be a scattering angle after the process. Scattering situation is the ideally suited to be analyzed with post-Minkowskian approximations, as we will hear very much in this week. When the two black holes are bound together, so on some bond orbit, the post-Minkowskian expansion actually reduces essentially to the post-Newtonian approximation. And again, there is a very nice overlap here, which has been checked very much with the recent result for the post-Minkowskian approximation, which computes the Hamiltonian of the motion, the conservative part of the motion, and which has been compared with high-order post-Newtonian predictions. Actually, this overlap is very fundamental. The best post-Newtonian approximation, this was recalled yesterday by Thibault, starts actually from a post-Minkowskian expansion, and each of the coefficients of the post-Minkowskian expansion are then re-expanded in a post-Newtonian way. So the overlap is very clear. If you have the post-Minkowskian Hamiltonian to some order n, say, then you are able to control the post-Newtonian expansion, the complete post-Newtonian expansion up to order n-1. So this means that if you want to compare to 4 Pn equations of motion, you need in principle to control the 5 Pm Hamiltonian. But on the other hand, obviously with the 3 Pm Hamiltonian, you will control many powers of V over C that are well beyond what can be computed with the direct post-Newtonian expansion. So the overlap is very interesting between the two methods. On the other hand, Thibault mentioned also yesterday the so-called multipolar post-Minkowskian expansion. This one starts from a post-Minkowskian expansion. So assuming that I have a source which with a small capacity parameter, so weak field source, and the principle of this method is to compute the post-Minkowskian approximation in the exterior zone of my system. So here I have on the horizontal axis the distance to the system, and on the vertical axis, as before, I have my ratio m over r for m over a for my system. So I compute the post-Minkowskian expansion in the exterior of the source for r larger than a, the size of the source, by expanding also or by parameterizing each of my post-Minkowskian coefficients by means of multiple moments. So this will be valid in the exterior of the source up to infinity. And at infinity, you can identify what are the observable in the field at infinity and what will be detected by your gravitational wave detectors. On the other hand, this method is just confined to the exterior region of your source, but then it can be completed by a matching to the post-Newtonian expansion inside your matter source. And if the matter source is a post-Newtonian source, that is, there is a small parameter V over C, then the domain of validity of the post-Newtonian approximation will overlap with the external part where you can perform a matching. So this is a powerful method, and this is a method which has been used to compute the Pn parameters that are used in the gravitational wave templates. So the Pn parameters come from a mixture of conservative and dissipative effects through the energy balance equation. You will compute first your conservative energy from the conservative equations of motion or conservative Hamiltonian of your system, and then use a wave generation formalism to obtain the energy flux at infinity and use this balance equation. For simplicity in this talk, I will consider only quasi-circular orbits. So there is only one balance equation to be considered, but actually the formalism has been computed for any orbit, eccentric orbit, and so on. So from this balance equation, you deduce the orbital frequency and then the orbital phase by integrating the orbital frequency, and you obtain a post-Newtonian result for the phase evolution, that is for the chirp, which is a post-Newtonian series. The dominant coefficient of that series will be the Newtonian approximation, which is the Einstein quadruple formula, and then there will be plenty of parameters, Pn parameters, that are just polynomials in the mass ratio of your system. And at some high order, there will be log terms and powers of log terms, and I will come back on this later in the talk. So for the moment, the Pn parameters for non-spinning binary, compact binary systems, They have been computed, as I was saying, with the multipolar post-Minkowskian PN matched approach. They are known up to 3.5 post-Newtonian order beyond the Einstein quadrupole formula, which is the first coefficient. There will be a correlation 1 PN, 1.5 PN order. This is associated with tails. I shall come back to this point later also in the talk. At some point, there is a log term which is at 2.5 PN order. However, this log term at 2.5 PN order is not completely a genuine log term. It comes just from the integration of the orbital frequency to get the orbital phase. But at 3 PN order, there is a genuine log which appears, which is associated with high order tail effects. Now, different approaches are used to compute the post-Newtonian approximation, and I'd like to make comparison and to use a synergy with the effective field theory approach. So we have the fundamental Einstein-Hilbert action to solve. We shall choose, for instance, harmonic coordinates. So we add a gauge fixing term to the Einstein-Hilbert action, and we shall use point particles for description of our system, using an effective description of particles by point masses. So with the traditional PN approach, we compute the Fokker action by inserting an explicit iterated post-Newtonian solution of the Einstein field equations that are obtained from varying the Einstein-Hilbert action. And this solution is iterated in a post-Newtonian way, and therefore depends on the matter variables, that is position, velocities, accelerations, and so on, that come from the matter part of the action, which describe our system of n point particles. And by inserting back this explicit solution into the Einstein-Hilbert action, we obtain the Fokker action for the dynamics of your particles. And then, if we want the radiation field, we shall vary the action with respect to the metric in order to get the stress energy tensor and insert the stress energy tensor into a wave generation formalism, computing multiple moments and re-expanding the field at infinity so that we get the waveform. On the other hand, the effective field theory will use the effective action, which is obtained by integrating over the gravitational degrees of freedom. Furthermore, the effective field theory will use diagrammatic expansion, and the diagrams will be computed in the Fourier domain. On the other hand, in traditional PN approximation, we compute everything in the real space domain, in real space, and we have a different language. We shall consider the emission from a quadrupole source, and then there will be nonlinear effects, tails, nonlinear memory, radiation reaction, tails in radiation reaction, which all have correspondence in terms of diagrams of the effective field theory. For instance, the tail effect will correspond to a graviton, which is emitted by my quadrupole source, and then scatters off the static potential associated with the total mass of my system, and then will escape to infinity. And then there will be also a tail effect in radiation reaction corresponding to a graviton which is emitted and then reabsorbed by the particle, and then will also, in the meantime, interact with the static mass, with the static potential associated with the mass of my system. And the two approaches are completely equivalent at the level of three diagrams. That is, we shall neglect in the effective field theory completely the purely quantum loops in the diagram, which means that the graviton lines are always attached either to the particles or escape to infinity. This is illustrated by the gravitational tail effect. The tail effect in this formula, which comes from a series of papers with Thibault in the end of the 80s, the tail effect there is an effect in the far zone and there is an effect in the near zone. In the far zone, this represents a small correction, which is due to scattering of linear waves of the background, the curvature background generated by the mass of the source. Okay, so this is a coupling between the, say, the quadrupole moment of the source and the mass of the source. Okay, which modifies the waveform at order 1.5 pn 1/c3 beyond the Einstein quadrupole formula, and the modification is given by some non-local integral extending over all the past of the source, integrating over the component of the quadrupole moment of the source in dominant approximation, and then there is a coupling with the mass. On the other hand, there is an effect also in the near zone, which is described by this diagram, as I was saying, which is a 4pn effect, because this is 1.5 pn order beyond the dominant radiation reaction, which is 2.5 pn order. And this effect can be described by a modification of the Fokker action for the dynamics of your source at 1.5 pn order beyond 2.5 pn order, which is 4 pn order. And again, this corresponds to a non-local action. Because of these double integrals, there is one integral for the action versus the Lagrangian, and then there is this non-local integral, exactly as in the effect in the far zone. Notice that, as we proved in this series of papers, that the two effects in the near zone and the far zone are completely consistent. That is, the radiation reaction in the source will be modified by this tail effect, and this radiation reaction will work, and then there will be a flux associated with this work, and this flux is completely consistent with the flux that you can compute directly from the waveform. So there is the nice energy balance also, of course, for all these high-order nonlinear effects. So if we have the PN parameters, and the tail effect in the PN parameter starts at 1.5 PN order. There will be next to leading tail effect at 2.5 PN order, next to leading effect at 3.5 PN order. And already in the known parameters, which have, by the way, already been checked by LIGO Virgo experiment detections, there is also higher order tail of tail terms. The tail of tail term give you a contribution starting at 3 PN order and involving, in particular, a logarithm, which is a genuine logarithm, which appears in the flux of gravitational waves at 3 PN order due to this tail of tail. The way we compute these high order tail corrections is to compute the observable of the wave at infinity in the form of a quadrupole moment, which is directly observable at infinity, which is a so-called radiative moment, okay, which will reduce to the dominant, to the source moment at the lowest order. Okay, but there will be correction due to tails, memory effects, which I will not discuss and refer to the previous talk for that. And then there will be the 3pn tail of tail integral, okay, and then the 4.5pn tail of tail integral, which is an effect which arises at 4.5pn order. So not so far from the 3.5pn order, which is known now and which has been checked partly by LIGO Virgo observations. So it would be very nice to extend the computation to include all the terms up to 4.5 PN order, but already at 4.5 PN order, the effect is entirely, or at least in the flux for circular orbits, again, the effect is entirely due to this nonlinear tail of tail interaction. And so the effect to the phase evolution is given entirely by these terms. This can be proved very easily from the calculation. And it will be nice, as I was saying, to obtain the 4pn term, which is more difficult. for the moment, which is known only using black hole perturbation theory. Therefore, in the test mass limit, nu tends to 0. This is known from works on black hole perturbation theories by the Japanese school, essentially in the 90s. And so from this work, we know the leading order terms in the phase evolution, but this should certainly be confirmed by traditional PN calculation, as well as computation of the corrections due to the finite mass ratio corrections to that signal. And so this is a goal presently. In order to reach the goal, or at least to progress in this goal, we need to refine our computations of the source multiple moments of the compact binary system. The source moment, or the quadrupole moment, is for the moment known at 3 PN order. So this produces these parameters up to 3 and 3.5 PN parameters previously. And we should extend the calculation of the source multiple moments up to, say, 4 PN order. So we have two types of multiple moments, mass type and current type moments. They are expressed in terms of closed form expressions, in terms of the stress energy tensor, pseudo stress energy tensor of the matter plus gravitation inside the source and extended up to infinity. So the integrals defining the multiple moments are actually extended on all space, and in particular at infinity, where they are typically divergent, and actually they are defined using a certain regularization, which comes from a particular way for iterating the solution in the multipolar post-Minkowskian approximation that we use for the external part of the field. And this process is to be used in the definition of the multiple moments consistently. And this involves parameter R0, which can be viewed as an infrared scale, which is in the problem and should be cancelled at the end in observable physical quantities. These expressions come directly from a matching, and I maybe say a few words on this matching later. So in this 4PN program, we computed the source quadrupole moment, mass quadrupole moment at 4PN order, using different techniques, and in particular, using regularizations. And we used for the UV divergences that are associated with the fact that we use point particles, so associated with delta functions, the delta function used to model the compact objects, in the spirit of the effective field theory, of course. And for the infrared, we use just the Hadamard regularization, which is defined by this regularization in ordinary 3 dimensions. So we obtained a result. This result depends on arbitrary constants, which are either UV or infrared scales. Remind that all these quantities are completely gauge dependent. Some people may say that it's a drawback of the method to have gauge dependent quantities. Me, I think this is an advantage, because with gauge dependent quantities, you can have many checks on intermediate step of your calculations. For instance, you will check explicitly that this constant cancel out at the end. So this expression of the source mass type quadrupole moment of a compact binary system at 4PN order is actually not complete, because it should be corrected by dimensional regularization for the infrared. That is, we should replace our regularization at infinity here by really dimensional regularization, and keeping still this B parameter process, this finite part when b tends to 0 as well. And this is a work in progress. And let me tell you where we are exactly in this problem. We have proved that adding correction due to dimensional regulation for the infrared divergences gives you poles already at the 3pn order. These are associated with this scale, infrared scale at 3pn order already, and there are other poles at 4pn order. And we have proved that these poles are exactly cancelled by poles coming from tail of tails contribution. So we have to consider the observable moment, which is a radiative moment, which is a source moment plus nonlinear tails and tails of tails. And then we have checked that at 3pn order, the poles properly cancel. And furthermore, the finite part beyond the pole exactly cancels a surface term, which is needed with Hadamard regularization. So, but which is not, which is absent in dimensional regulation. So we have proved that at 3pn order, actually, the moments can be computed only with Hadamard regularization and an ordinary 3D computation of nonlinear effects, tails and tail of tail. So this is quite satisfying, but this is limited to 3pn for the moment. There are still remaining poles at 4pn order that are associated with a nonlinear coupling, cubic nonlinear terms that are associated with the tails of memory tails that were mentioned by in the previous talk as well. So we have to control all these nonlinear cubic terms in order to check that the poles indeed properly cancel out, but this is work in progress. On the other hand, we need also the 3pn current type quadrupole moment. Since this is 3pn, we think by the previous calculation for the 4pn quadrupole moment, mass quadrupole moment, that at that order, it is sufficient to use dimensional regularization for the UV, but also only Hadamard regularization for the infrared. Then for this problem, we need to use dimensional regularization. That is, we need to define the current type moments in d dimensions, which means that we need to define the decomposition of tensors in d dimensions into irreducible pieces, which is not completely trivial because we don't have at our disposal the usual Levi-Civita symbol to define the current moment. So we have to do a generalization of this irreducible decomposition. And doing this, we find that the mass type moment are given by usual symmetric trace-free expressions.
So Luc, I just want to point out, you've been speaking for 31 minutes and you're about halfway through your slides. I just want to tell you.
Okay, thank you very much. And then, in addition, we have to generalize the current type moments, which involve then, in d dimension, two tensors, which have the symmetries of non-trivial mixed Young tableaus, as illustrated in this formula. And then, from that, we can obtain the gravitational wave modes associated with the current quadrupole moment, which is the mode H21 to 3pn order, which will correspond to an effect in the waveform at 3.5 pn order. Okay, so let me now come back to the effective description of compact binary systems. So, and this is very much also emphasized by people from the EFT community. We have a hierarchy of length scales in a compact binary system. We have the size of the system, which is small with respect to the wavelength of the emission of waves. And then we have our compact binary systems, with the size of the two neutron stars, say, which are very small with respect to the orbital size. And then at Newtonian order, we have also an effective action which will go beyond the point-particle approximation to include contributions due to quadrupolar tidal effects. If I denote by G the external tidal field felt by each of the bodies, if I neglect the tidal dissipation, that is, I assume that the quadrupole moment of my bodies stay aligned exactly with the tidal field generated by the other bodies, then I can write a Lagrangian, an action at the Newtonian order, which corrects the point-particle action by some extra terms. And this is obviously in the spirit of the effective description. At the lowest order, we know that this will correct the effective action by a term which is small for compact objects, in the sense that the chirp will be modified by a contribution which has the same formal order as a 5pn orbital effects. But the coefficient in front of that effect will be a very large number typically, and this has been already checked by LIGO-Virgo. The coefficient is a combination between the two polarizability parameters of the two neutron stars, and this has already been checked by LIGO-Virgo, which could exclude some equation of state. The stiffest equation of state were excluded by this test. And there have been many works on defining the effective field theory action for extended compact objects. And then we can extend by the point-particle action by a series of non-minimal word line couplings, depending on tidal multiple moments defined with the Riemann or the Weil tensor and its covariant derivative and projected onto a local tetrad following the word line. And then there will be the polarizability coefficients associated with the object. And there are two series of these. Just to mention our recent work on that. So there has been a lot of works trying to extend this contribution due to tidal effects in the chirp, in the phase of the binary system. And our recent result with Quentin Henry and Guillaume Fay is the completion of the orbital phase, say in the stationary phase approximation, at the next to leading order for compact binaries on circular orbits. And so this is the next to leading order. So the leading order is a 5pn term, but there is a big coefficient associated with the internal structure of the neutron star, depending on the equation of state and so on. Then there will be the next to leading order, and then there will be tail effects. And we have checked that the PN conservative dynamics associated with that is consistent with recent post-Minkowskian tidal derivation for the Hamiltonian computed with scattering amplitude.
So Luc, you've now been speaking for 36 minutes.
Okay, how much minutes do I have?
Well, we should end about in 40, about 4 minutes left.
Okay, very good. So to end this presentation, I would like to come back on the near zone, exterior zone split in post-Newtonian expansions. So in the multipolar post-Minkowskian and PN matched approximation, we shall have a multiple expansion in the near zone, in the external zone, and a post-Newtonian expansion in the near zone. And these have to be matched in order to obtain the expression of the source multiple moments that are here, and in order to obtain radiation reaction effects that are there. And the matching can be done quite generally using a matching equation. Okay, M means the multiple expansion and the bar means the post-Newtonian re-expansion. And the general solution of that matching equation, I will skip two lemmas that are convenient tools in order to get the final solution. And the final solution is completely general. It gives you the multiple expansion in the far zone at any order in post-Minkowskian expansion and any order in post-Newtonian expansion as a functional of the source multiple moments that are known as integrals over the source. That was the formula that I showed you before. And on the other hand, this gives you a complete general solution for the near zone field expressed in a post-Newtonian expansion, formally valid at any post-Newtonian order. This last expression in the language of effective field theory is made of potential modes and radiation modes. Potential modes are responsible for conservative near zone effects, okay, and they are computed with a symmetric propagator. And the radiation modes are conservative effects coming from gravitational waves propagating at infinity, the tails. And some recent work has shown that this split between potential and radiation mode is exactly the same as the one used by effective field theory. Namely, if you compute using the traditional PN approximation the radiation mode, you find that this corresponds to tails, okay, and that these terms, which is actually the second term here, is exactly equivalent to a Feynman diagram derived by the EFT community, and the agreement is completely exact. That is, this decomposition is exactly the same as the one used by EFT. And this gives you equivalence between the post-Newtonian theory and the effective field theory, at least at 4pn order. So in the limit epsilon tends to 0, you obtain the Hadamard Parti-Fini integral with a pole, okay, and the pole will be cancelled by an infrared pole coming from the potential mode, and then we end up with completely ambiguity-free derivation of the 4pn equations of motion that are completely equivalent between Pn and the effective field theory.
So, Luc, you've now spoken 40 minutes.
Okay, so maybe it is good that I stop at this point and can answer question.
Okay, thanks a lot. And sorry about being a little brutal, but you know we have people from many different time zones. You know, so we have to stick to the schedule.
Of course, of course.
Let's see if there are any questions or comments. Again, I have difficult. I see there is no. That's Barak who already. You just did not. You still have raised a hand. Maybe I can ask a quick question. Your cancellation of your what you call R0 and R0 prime, they cancel, but they're inside a logarithm. So if they cancel, they must be replaced by some physical scale. Is that GM or what replaces R0?
Yes. So this is actually the next slide. So if you consider the source quadrupole moment, say at some order, 3pn order, you find that there is this scale. Okay, and inside the logarithm, there is a distance between the two compact objects, R1, 2. Okay, on the other hand, in the far zone, you have the same scale, R0, and here this is a scale tau, which is integrated over all the past, and so the two constants cancel out, and actually inside the logarithm, it remains the physical distance between the two objects.
Times tau, which is then integrated over.
Yes, and there is
divided by tau.
Yeah. O, which is the variable of integration.
Yeah. Okay, thanks. All right, I'm sorry. I think we need to cut it here. Thanks again, Luc.
Thank you very much.
Starts in it's 4:45 in Central European time. So this is about 10 minutes where we can all stretch our legs. So be back in 10 minutes, please. So, Harald, you're here?
Yes, I am here.
Good. Yes, you have two aliases, it seems.
Okay. Now I
so-
should be. You should hear me without echo.
And now you're on the as co-host, so it's correct. Yes. Okay. Very good.
Okay.
Mhm.
Yes, I've also decided to log in with my laptop just to double check whether
Good. That's good. Thanks for doing
everything works and
Exactly.
especially
I'm grateful for that.
whether the mouse is visible. That's always
Exactly.
the exciting question.
You're not doing full screen. I guess you know that. You're not doing a full screen presentation.
I didn't intend to.
Okay. Okay.
Do I have to?
No, it's it just becomes a little bit bigger, but we can see now your full screen. I mean, we can see your monitor actually, right? But that's because on purpose.
This was not on purpose.
Ah, okay.
Let me try this again. I wanted to do this one here.
Yeah, this is better.
This looks better. Good.
Yeah.
Perfect.
And just check also that you can scroll just maybe one slide. Right. Yeah, and you have a pointer by chance?
And I have a pointer.
Yeah, excellent. Very good.
Excellent,
All right.
excellent.
Well, we're all set then, but we wait
Looks
just
all
a minute.
good.
So I will do what I've been doing in the talks. I warn after 30 minutes, just for you to have the time. And then you can, it's up to you whether you want to talk 4 minutes or 5 minutes or maybe up to 10 minutes more. That means we cut the discussion, unfortunately, if you speak more. So it's a little bit up to you. Good.
Paul, sorry to interrupt, but in principle, Sebastiano should chair Harald at the moment. Sebastiano.
She's not chairing anymore.
Yes.
Even better. Okay, very good. All right. Well,
Organization is always.
I will listen to the talks. Okay, very good. Okay.
I don't mind. You can also do it.
No, please. So I check out, but I mean, I will stay with the talk, of course.
So shall we start now or we wait 1 minute?
So I guess that needs to decide whoever is going to chair.
Okay, there are 62 people that look connected. I think I can introduce you and then we can start, I think. I don't know what this means, this small cloud close to the participant chat. Anyway, okay, let me introduce Harald Pfeiffer. So Harald got his PhD at Cornell University. He was a postdoc at Caltech. He then was permanent at CETA in Toronto. And since 2017, he is a group leader in the numerical relativity group of the Albert Einstein Institute. I think he will be talking about binary black hole simulation with the spectral Einstein code or the SXS collaboration, which he contributed to found and for which is expert. Yeah, we see your screen. I think you can go ahead.
Okay. Thank you very much for the introduction and thank you for the invitation to speak here. This talk is about black hole simulations with one of the many codes that exist, the spectral Einstein code. Let me start with some motivations to remind you that waveform knowledge is essential for gravitational wave astronomy. The gravitational wave detectors detect signals by matched filtering, which requires the waveforms. Parameter estimation compares the measured data with the predicted waveforms and checks where the region where there's consistency. Tests of GR requires to know the prediction of general relativity, and validation as well is a very important part, that one injects a synthetic signal into LIGO noise and makes sure that one actually recovers consistent data and consistent parameters from the LIGO pipelines. As Alessandra also already pointed out yesterday, for today, it appears like all our waveform models are good enough. However, in the future, we need higher accuracy for more diverse systems. The left plot here illustrates the expected signal-to-noise ratio versus a redshift distribution for third-generation detectors on the left of the plot and for LISA in the middle of the plot. And you see that the huge areas that are red color-coded, this is where signals could be detected with signal-to-noise ratio of 200 or above, much more than the current LIGO events. And the right plot serves to remind you of the variety of sources that LISA is sensitive to, starting with supermassive black holes over extreme mass ratio binaries, intermediate mass ratio binaries with eccentricity, with spin, with precession. Essentially anything can happen in LISA. The tools for waveform modeling, very simply put, depends on where you are in the stage of the inspiral. The early inspiral, post-Newtonian theory and post-Minkowski and EOB methods are ruling the toolbox. The late inspiral and merger can be done by numerical relativity, and black hole perturbation theory for the ring down, and perturbation theory in mass ratio for extreme mass ratios. The importance here of numerical relativity comes in that it is the only method that can connect on first principle the inspiral with the ring down for merging binaries. And it also happens to be the predominant method in that region of parameter space that is most relevant for the LIGO black holes, the last 10, 20 orbits of inspiral for comparable mass ratio systems, at least so far. Numerical relativity has a long history. It dates back to the 60s. Here's a plot that I made 5 years ago trying to collect various contributions. I stopped in 2015 doing this plot and updating this plot. The slide was full. And the thing to highlight here is between 2005 and 2008, the breakthroughs in simulation capabilities, first by Franz Pretorius, then followed by the RYT group and the Goddard group, and then somewhat later, the spectral simulations of the SXX collaboration. Just to remind you how this very early waveforms actually looked like, they had essentially no inspiral at all. You saw the merger waveform in the ring down. Very quickly, the waveforms became a little bit longer and had a few inspiral cycles, but certainly nothing like the embarrassment of riches we are finding ourselves in today. But already these very early simulations showed a very important result, the simplicity of the merger dynamics of binary black holes, that there's a continuous transition from inspiral to ring down. And it's that simplicity that makes all the waveform modeling possible and so successful these days. By now, there are two major approaches for binary black hole simulations in use. And curiously, they differ in basically any single choice they make along the way. The more widely used approach could roughly be called BSSN in moving puncture. The approach I'm going to talk about later today goes under the name perhaps generalized harmonic and spectral. So there's quite a few codes in the BSSN in moving puncture camp. There's only the spec code on the right-hand side. The type of initial data is different, puncture initial data, quasi-equilibrium. The evolution The formulation of the evolution system is different. The formulation for the treatment of the black holes is different, with punctures on the one side and black hole excision on the other side. Outer boundary conditions are implemented differently. The numerical methods are different. In one case, the black holes tend to advect through static grids. In the other case, the grid actually moves smoothly along with the black holes. And there's also differences in how gravitational waves are extrapolated, extracted, and post-processed. I'm highlighting here in green the perhaps most dominant distinguishing features. The type of initial data determines how high spins one can achieve. The type of black hole excision, black hole treatment depends whether it's easy or difficult to do the merger itself. And the combination of good outer boundary conditions, spectral methods, and the moving grid is what enables SPEC to do the long and the highly accurate inspirals that I'm going to talk about during the rest of the talk. And also, we have quite a bit of new gravitational wave extraction technology that I also highlight later on. Perhaps curious, there's one code that doesn't fit as closely into this left-right split, and this is actually Franz Pretorius's code that uses pieces from the left and pieces from the right, and his own individual source as well. Okay, let me now turn over and focus more on the results we have obtained with the spectral Einstein code. When I say I or we, henceforth, I mean the simulation extreme spacetimes collaboration that grew out of Caltech and Cornell and has since then expanded to encompass quite a few more institutions, depending where people move to, including, of course, the Albert Einstein Institute, where I am now based. It's a big code, about 700,000 lines of code, developed over about 15 years with order 100 or so contributors over the years. Spectral methods in a nutshell, the basic idea is that you expand the solution in basis functions. So you have a function u of x and t, you expand them in basis functions phi k of x with time-dependent coefficients in front. Kind of like a Fourier transform of data as opposed to the discrete points for finite differences. One of the immediate advantages this gives that derivatives can be evaluated exactly because we know the derivatives of our basis functions, Chebyshev polynomials or similar. And that way we can evaluate the partial differential equations exactly as well because we know our basis functions so exactly. The approximation comes in by the truncation in the number of basis functions n. And if everything is done right and the problem is smooth that is to be solved, spectral methods result in exponential convergence. That's the one biggest advantage of these methods. We combine this with a domain decomposition that uses spherical shells near the two black holes, cylinders and cubes at intermediate distances, and more spherical shells at large distances going out to our faraway outer boundary. So this has the advantage that we can excise the black hole singularities, we can place adaptively resolution where it's needed, and we can also parallelize by putting different elements on different compute cores. There's a lot of beautiful formalism behind numerical relativity, both in the initial value problem and in early results about how to make good binary black hole initial data. There's also even more formalisms that underpin the evolution equations and their reformulations, including Franz's breakthrough work in 2005 that enabled simulations. So I have more time for results. I'm going to skip all these technical details, but I'm happy to come back to them later on during questions if people are interested. Black hole excision is an important part of our code. So let me briefly highlight. The idea is that inside the event horizons, we can place an artificial boundary in this top right panel indicated in red. because in the generalized harmonic evolution system, all information propagates within the light cone. That means this red boundary is a perfect outflow condition, and we don't require any boundary conditions there. One downside is we need to deform our inner boundary of our computational grid to actually match the deformed apparent horizon shapes of the black holes, which near merger for unequal masses with spin, this can become quite extreme, like in this diagram in the bottom left. Highlighting a different aspect, outer boundary conditions. In the very long simulations we are doing these days, the outer boundaries are causally connected. And therefore, these boundary conditions become ever more important in order to avoid difficult to detect problems coming in. The SPEC's boundary conditions are both constraint preserving, so no constraint violations enter, and they are also minimally reflective, letting gravitational waves pass to the exterior quite easily, but not leading to many reflections. The primary work on these conditions were done by Lee Lindblom and Oliver Rinne in the 2000s. Here's one example of how this works. If you focus on the blue curve here, this is a mass ratio 6 simulation, about 20 orbits long. And it's actually run twice with 2 different distances to the outer boundary, actually 3 times. And the top panel shows actually the waveform, the nice usual chirping behavior. The bottom panel shows the difference in the gravitational wave phases between the 3 simulations with 3 different outer boundary radii. And you see the outer boundary only matters to the tune of perhaps 0.01 radians or so of the gravitational wave phase. And putting all these things together led to the standard SPEC approach that we have now been using for approximately 10 years. The top left panel shows the first important complete waveform we obtained, a 15-orbit inspiral equal mass no spin. Both panels up and down show the same waveform. They only differ in whether the vertical axis is linearly or logarithmically placed. In the bottom panel with the logarithmic placing, you see the very nice exponential ring down for about a factor of 10 to the 4 in dynamic range. Again, owing to the spectral methods. The right panel is particularly important here. This is a convergence test. We have run the simulation at 6 different resolutions, and that way we can assess the phase errors of all these resolutions by comparing against each other. At low resolution with 42 cubed basis functions, we find errors of about 5 to 10 radians. But by only increasing the resolution a factor 1.5 per dimension, we can suppress the error by a factor of 100, reaching 0.01 radians during the inspiral and 0.1 radians even including merger and ring down. And these high precisions, just to repeat this point, are made possible due to the spectral methods. They lead to the rapid convergence, but spectral methods by itself doesn't tell you about the overall constant of proportionality in front. And this one is particularly small due to our use of moving grids that avoid having to advect the black holes through a static grid. One slide I have been showing for many years now is this very nice comparison early on with post-Newtonian techniques. So plotted here on the y-axis, the difference NR to post-Newtonian methods. And the curves plotted here right now are at second post-Newtonian order, show fairly large differences. As I go up in post-Newtonian order, the methods converge to each other. An important validation for the numerical method, but also for post-Newtonian, that way giving an estimate of how accurate the post-Newtonian waveforms actually were. The 4 different curves correspond to 4 different flavors of post-Newtonian, in this particular case, various tailored time domain approximants. Okay, having laid out the technology of SPEC and also having also working code by our collaborators in other groups, the community began exploring the parameter space of all possible binary black holes. The plot showing right here is the state of the art, all the 20 waveforms worldwide that were known by 2009. And then the field pretty much exploded. Our first SSX catalog had 170 simulations, and you had to zoom in order to actually see the waveform cycles. And we have continued doing this. Second catalog in 2015. It was used to improve aligned spin EUV waveform models. And then more recent processing simulations have then, for instance, been used to calibrate the more modern V4 EUV models, including the V4 PHM waveform model that Alessandra talked about yesterday. And that is also one of the primary analysis tools for the gravitational wave detectors these days. Our current public catalog has about 2,000 simulations, and it has very good coverage up to mass ratio of 1 to 4, and some coverage above. The biggest mass ratio we have public is a mass ratio 10 non-spinning simulation. I'm not talking too much about high mass ratios today, because I want to get to hyperbolic scattering simulations, and because I assume Carlos Lusto is talking about them in great detail when he's talking in a day or two. All the simulations come at multiple resolutions, and this is crucial in order to assess the numerical errors. For instance, the top right panel here shows the typical mismatch we get when we are comparing medium and high resolution of our simulations. So typically 10 to the minus 3 to 10 to the minus 4, but some outlier up at 10 to the minus 2, and some particularly good one at 10 to the minus 6. If you remember Alessandra, just to give you a context of the axis range here, the current goal of waveform modeling is to be good to 10 to the minus 2 or below. And with advanced detectors, we need to go down to 10 to the minus 4, 10 to the minus 5. So many of today's simulations actually aren't yet good enough for the future, and probably aren't long enough either. Besides us, of course, several other groups are also doing parameter space exploration. Here's a list of various waveform catalogs. Just highlighting, biggest mass ratios come from the RIT group currently. The biggest spins, 0.995, come from the SXX group. The longest simulations are also coming from the SXX group with the spec code. So these are the results. And these are results obtained with the code I'm talking about. The main use for these simulations obviously are the waveform models, because we have the gravitational wave detectors operating. They are finding gravitational waves quite regularly, and we want to extract as much science as we can. Current waveform models have precessioned higher modes, but not yet eccentricity. They are EOB models and phenom models. And more recently, numerical relativity surrogate models also came up and joined the fray. Those surrogate models are quite different. They directly construct the approximating functions from the NR simulations themselves. They need about 1,000 NR simulations to work. And so the big catalogs, like the 2,000 ones we have now, were actually truly instrumental in doing that. And once one has worked out all the little details of how to go from the simulations to a model, the model construction is almost automatic. So when new simulations come along, it's fairly straightforward to upgrade the surrogate model to either become more accurate or to expand in parameter space coverage to the bigger parameter space of the newer waveform simulations. The model accuracy can also reach the accuracy of the NR simulations. So all of these are really good properties. However, the surrogate models work only where numerical relativity is available. So there's a limitation on parameter space coverage. And that this also implies a limitation on length. About 20 orbits, 40 gravitational wave cycles is the state of the art. And anything earlier in the inspiral still requires and will continue to require analytic early inspiral models or analytic models at higher mass ratios and higher spins. A brief overview of what the current records are in terms of parameter space. For spins, it's 0.998 for equal mass and 0.95 for unequal masses by the SXX collaboration. For mass ratio, it's now 1/128 by Carlos Lusto and Jim Haley. I am pretty sure Carlos will talk about this when he's speaking. As far as duration, the longest published one is 350 gravitational wave cycles at mass ratio 1:7. And the earlier mass ratio 6 simulation I told you about for the outer boundary test is plotted here at the side. It's this little thing at the right. The simulations are so long that you can't really see any individual cycles anymore. In terms of as generic as possible, we have run a few years ago both eccentric and precessing simulations at fairly high mass ratio that have trajectories that look quite similar to what you would expect from the geodesics. Quite fun to do those simulations as well. Okay, let me now switch over after this general overview of what has happened in the past, excuse me, and give you some more recent results of either already completed work or still ongoing work, just to give you a sense of we are not done with these calculations and life is progressing at a rapid pace still. One important topic of improvement were how we are computing the gravitational waves based on the simulations we have. It turns out the gravitational wave extraction is one of the limiting features that determines how accurate we can do our gravitational waves. And so there have been several different related improvements in how gravitational waves are done. A simple to understand one is a correction for the center of mass of the binary black hole simulations during the inspiral. So typically, if you start an NR simulation, the center of mass doesn't just stick at the origin, say up here, but it drifts ever so slightly in some random direction during the inspiral. The drift is very small, perhaps 0.01 or 0.02 m during a long spec inspiral. But nevertheless, because gravitational wave extraction spheres are centered on the origin, that already introduces weird features into higher order mode. Like here in orange, the 2-1 mode shows these oscillations that shouldn't be there. Since 2019 catalog, we correct for these oscillations for the center of mass drift, and this actually removes the predominant part of these oscillations. And for instance, here the 2-1 mode now looks very nice and smooth as expected. More recently, we now have code to extract all Weyl scalars from psi4 all the way down to psi0, albeit psi0 and psi1 are by far the most difficult to extract because they decay so quickly with distance. And we have also worked on improving the reducing the impact of the initial burst of radiation that is produced by all numerical relativity simulations. So down here is a plot of a 4-4 mode of some simulation. And typically what you're seeing is some burst of noise early on that arises because the black holes are not in perfect equilibrium in their initial data. And so there is some quasi-normal ringing coming from the black holes and some relaxation of the space-time around the black holes as it settles down to its best possible equilibrium state. So ways to deal with this better are, number one, to improve the conformal data we use for the initial data. That leads to the improvements shown here, where the best one doesn't have any visible chunk radiation there anymore on the scale. But we're also clipping away the burst by resetting the outer boundary, and we split numerical resolutions after the burst of gravitational waves has left, both of which also improves the accuracy and fidelity of new simulations we are doing. Cauchy characteristic extraction has been a significant focus of work at Caltech and at Cornell, led by Jordan Moxon and early on Kevin Barquette and Bela Szilágyi, as well as Mark Scheel. my collaborators have developed a new Cauchy characteristic extraction code that is actually fully spectral and is both faster and much more accurate than the standard Cauchy characteristic extraction code beforehand, the bit null code. The diagram here in the top right panel illustrates the idea of Cauchy characteristic extraction. The red area here indicates the area covered by a usual Cauchy 3+1 numerical relativity code. It has some outer boundary radius, typically 500 m to 5000 m away, and it only computes the solution of the spacetime inside its outer boundary, obviously, and so it only covers the region near the center of the spacetime conformal diagram. Cauchy characteristic extraction is now a post-processing step that takes data from somewhere inside the 3+1 evolution code and evolves Einstein's equations from there out all the way out to future null infinity. So the output of Cauchy characteristic extraction are waveforms at future null infinity in a well-defined gauge adapted to future null infinity. And this output can be achieved fairly independently of what coordinates the NR simulation uses in the interior. The bottom panel here shows a test of a null test. So what's being done here is a Schwarzschild black hole is put into the computational grid. And via a coordinate transformation, the Schwarzschild black hole is moved periodically left and right. And shown here in black are the resulting gravitational waveforms extracted by the pit null code. They're already quite small, 10 to the -5, and decaying with resolution. And shown in colored here are the extracted gravitational waves from the new spectral implementation of the SSX collaboration. They're starting at 10 to the -9 and rapidly decay down to 10 to the -11. So it's more accurate, while at the same time also being a lot faster than the bit null code. In this particular case, because we're only having Schwarzschild with the coordinate transformation, the correct answer is 0. And actually replicating this is a truly significant test for any wave extraction scheme. Quite new, there has also been more work from the Cornell group at utilizing the BMS balance laws and to compute gravitational wave memory. So the balance law equations we are using are in the formulation of Pasteca 2020. And they basically are consistency conditions that the waveforms must satisfy at future null infinity. So the waveform right now must be consistent with a certain time integral over all of the past of the waveforms arriving there before. In numerical relativity, of course, we can't reach the infinite past, so we need to truncate at some finite early time. And we have to account for anything that was accumulated beforehand by some constant offset alpha here that must then be determined with in some way. And using these balance laws, one can do two different things. Number one, one can do a validity test of how good the numerical relativity waveforms are, because the numerical relativity waveform should agree with the waveform that is obtained if one integrates up the balance law. And whether or not this is the case is a good thing to test. And then one can also use this balance law to actually improve the waveform, starting with an original waveform and then run it through this formula to get an improved waveform. Here's one example of what this does. It really helps with the one line selling point of this whole procedure is that the new gravitational wave techniques actually reproduce the gravitational wave memory correctly. The plot here shows a certain mode, the 2-0 mode of a certain simulation. And the standard result you get, if you look at any of the waveforms in our catalog, looks like the one below here. It starts at 0, you get some wiggles in the 2-0 mode around merger, and then it goes back to 0. The 2-0 mode, by the way, is the most difficult one to extract in numerical relativity because it is not oscillating during the inspiral. Similar features would do occur for all other waveforms we have ever computed. Like here, for instance, the waveform starts at 0, it oscillates, and then it goes back to 0. So what's missing here in both cases is the gravitational wave memory, which does lead to a small but noticeable offset from 0 after the gravitational waves have passed. In the case shown here in the top left plot, this is actually quite significant. So the actual gravitational waveform that is emitted by the system is the gray one here. That is the one that is extracted with Cauchy characteristic extraction. And that correctly has the gravitational wave memory, which has a particularly large component in the 2-0 mode. And so this entire offset is only accessible now via Cauchy characteristic extraction. Luckily, it doesn't matter for gravitational wave detectors today, because offsets are very low frequency effects, and gravitational wave detectors are not sensitive at those very low frequencies. So all is fine for gravitational wave detectors today. Using the balance law to correct the spec waveform, we can get from our standard waveform to the red dashed curve here that basically agrees very, very well with the CCE waveform, including memory. And this correction can apply retroactively to the entire catalog, and doing so is a work that is currently in progress. The bottom panel shows how well the resulting waveforms agree with the BMS balance law. The x-axis just labels 15 different ones. The y-axis is the violation of the balance law. The standard spec waveforms, as they're currently in the catalog, have violations of order 10 to the -2. The CCE waveforms are more like a 10 to the -6. And the corrected standard spec waveforms, hopefully to be published in the near future, actually get us down a significant way towards the golden standard, the CCE waveforms. As I said, very important work by the group in Cornell and Caltech around Keith Midman and Dan DeYotso are the two graduate students doing most of the work, as well as Kara from Ashteka's group. Another recent development is that we have looked back at harmonic coordinates, not to run simulations in, but to also compute along with the standard binary black hole simulation. The idea here is that also knowing the harmonic coordinate locations of the black holes gives us more information in order to make comparisons to post-Newtonian, to EOB, to scattering results. And for instance, what the harmonic coordinates immediately do is, here's a plot of coordinate distance versus time for a short inspiral. The harmonic coordinates look fairly smooth, the red curve here, whereas the standard spec coordinates that have a coordinate change about 100 m into the run lead to this extra offset that is then quite difficult to match to post-Newtonian, because spec by standard doesn't use the harmonic coordinate gauge, but a generalized harmonic coordinate gauge. A third recent improvement concerns eccentricity. Of course, eccentricity, now that quasi-circular black hole simulations are so well under control for today's gravitational wave detectors needs, are the hot topic a lot of macrorelativity groups are working on. The left panel here shows results by the Illinois group around Huerta. The right panel shows some results of Ramos-Boades and collaborators back when Ramos-Boades was still at Palma de Mallorca. So quite a lot of people are working on eccentric binaries, and of course, so do spec and we. And here's a few examples of the simulations we have obtained so far. As expressed earlier, our unique selling point are precisely the very long and very accurate simulations. And here's a sequence of equal mass non-spinning simulations. They start all at initial distance of 60. And depending what initial orbital frequency one is using, they either spiral in extremely rapidly and merge after a few periastron passages, or they go on for about 60,000 m and pass through 30 or 40 radial oscillation periods. And of course, with various commensurate eccentricities along the way. The lower panel is the important one. That shows a convergence test on the orbital phasing of these inspirals through all the 20 or 30,000 m of inspiral. And if you're focusing on the yellowish solid curve here, you see that for this 30,000 m curve inspiral, the errors are typically order 10 to the -2 during the inspiral, reaching around 10 to the -1 right at merger. So that's quite remarkable accuracy. And Ramos Boates has now extended these simulations, covering a much larger range of mass ratios and also systematically covering different spins. And also looking at putting a lot of attention to getting clean higher modes in the gravitational waves. It's actually remarkably more difficult to do this for the eccentric binaries because there's so much more structure in the gravitational waveforms than elsewhere. But we've now managed to get all the modes up to 6,6 very, very clean. And only the 8,8 mode at 10 to the -6 magnitude still shows various numerical noise artifacts. So things are actually looking quite good with these eccentric simulations. And in parallel to us preparing a paper about the simulations, of course, there's already work going on using these to calibrate and to construct eccentric waveform models for future LIGO needs. There's also a first eccentric circuit model that is built on spec runs. It only covers equal mass and no spin at all, and it only covers very small eccentricity. So it's more a proof of concept that this actually works, but eccentricity doesn't really seem to be a big impediment towards building surrogate models. Okay, in my last few minutes I have left, I'd like to talk a little bit more about binary black hole scattering. Because this is the topic of this conference, and because it provides another venue for how we can use and employ our numerical capabilities. So the typical black hole scattering effect is this. You have two black holes coming in, they scatter about each other by an angle alpha, and they go out again. And besides the scattering angle alpha, what is accessible in our numerical simulations is the energy and angular momentum emitted in gravitational waves, how much the velocities at infinity of our two black holes change. And we can also contemplate looking at the change of black hole masses and black hole spins when the two bodies interact with each other. You may not have noticed it the first time, but these black hole horizons actually are color-coded by the scalar curvature of their horizons. And you see near the point of closest contact, there's quite a strong deformation of the horizons being induced. Presumably, this will also lead to quasi-normal ringings of the individual black holes after the encounter, which then in turn changes the masses and the spins of the bodies ever so slightly. So all this information in principle is accessible in the numerical simulations, but so far we have focused our attention on the scattering angle. One important puzzle to make all of this work are actually the use of the harmonic coordinates that has recently become possible as well, because we need to extract coordinate trajectories to get the directions of the incoming and outgoing black holes. And we need to compare these coordinate trajectories to their post-Newtonian expansions in order to get the angles and the trajectories fitted accurately enough, given our finite distances at which we have to start and end our simulations. So the bottom panels here show two examples of data that we obtained from one simulation. The left-hand plot shows the post-Newtonian energies obtained by fitting at various post-Newtonian orders to our simulations. Encounter is at a time of about 600. So before the simulations have lead to quite consistent energy and quite constant energy, with higher post-Newtonian orders converging to a constant. Afterwards, the post-Newtonian estimates also lead to a constant energy. Again, convergently resolved, the higher the post-Newtonian order, the better everything looks and the more constant. And the jump between initial and final energy is, of course, the amount of energy lost in the scattering encounter. We can play the same game with the angular momentum. This particular simulation starts at 0.13, 0.14 and goes down to about 0.1, 1.0. And we can repeat all these things for many different simulations. And in particular, we can also fit the trajectories that we get out of here in the very early and very late part of the simulation to the post-Newtonian trajectories, in order to then use the post-Newtonian formulas to extrapolate the trajectories to much larger distances in order to get the asymptotic scattering angle. This is indicated in the top left panel here. If we do the fitting to first with 0th order post-Newtonian equations, Newtonian gravity, we find that we get a scattering angle that is actually off by about 10 degrees from performing these fits with post-Newtonian accurate expressions. Going from 1 to 2 to 3 post-Newtonian doesn't really matter much on the grand scale of this plot, where you're seeing several tenths of degrees on the y-axis. But certainly 2 and 3 PN is even closer together than the 1 PN, which you can still see a little bit offset from the main final results indicated by the big circles. The white two plots test to what extent our coordinate choice matters for the scattering angle. And they compare in both cases the scattering angle obtained by harmonic coordinates, as well as obtained from the straightforward generalized harmonic code coordinates we have. If you use initial data at separation of 50, there's a substantial difference. If you use initial data at a separation of 100, the two coordinate choices give us consistent scattering angles, and they also give us the same scattering angle as the simulation at distance 50. So overall, this shows that we have a good grasp on the importance of numerical resolution, on the initial conditions, whether we start at separation 50 or 100, on the impact of coordinates, and on our techniques, how we extract the scattering angle. And overall, we estimate our cumulative uncertainty to be below 1%. And if I say we, in this particular case, the important person doing these analysis is Hannes Rüther at the Albert Einstein Institute. And so our current best effort analysis is this one here, that actually tries to replicate the results that Thibaut Damour and collaborators obtained in 2014. What you're seeing here in the circles, the symbols, are Thibaut's old results from 2014, which we can now very well replicate with our new code. Our error bars are somewhat smaller than the Damour et al. Error bars, below 1 degree versus a few degrees. Not visible on the scale of this analysis, but it's definitely good that, and we find good agreement. And the important feature here is that this actually validates both analyses, both codes against each other, since the results were obtained many years separate with codes of very different architecture run by different people. So we are quite happy with these results. And here's also some first preliminary comparison to post-Newtonian and post-Minkowski results. And we hope to work more on these comparisons in the near future. Of course, whenever you're doing scattering angles, whenever you're making the impact parameter small and smaller, at some point you go from scatter to capture. And so the top panel of plots here shows a sequence of simulations at its smaller impact parameter that eventually leads to capture. And the movie in the bottom shows also a capturing simulation for unequal mass black holes. Simulation that starts with 2 unbound black holes that lose enough energy at their first encounter to then form a bound pair. How am I doing time-wise?
I think you are basically done.
Okay, perfect.
If you want to take questions.
Okay. Then I'll skip the fifth thing here because this is a topic I have already talked about before, that our simulations are accurate enough to actually reach high enough mass ratio and at high enough precision to make direct comparisons to gravitational self-force results. As I said, I've talked about this before at other meetings with a similar group. The difference is that the paper by now is published. And I guess the takeaway message is here: for the most simplest case possible, for non-spinning, quasi-circular black holes at a modest accuracy of about 1 radian, it turns out the mass ratio gap between numerical relativity simulations at comparable masses and gravitational self-force calculations that are traditionally viewed to concern the mass ratio regime of 1 to 10,000 or 1 to 100,000. It turns out there is no gap between these two methods, that the small mass ratio approximations, once the second order gravitational self-force results are put into them, with these second order gravitational self-force results, the small mass ratio approximations seem to be accurate enough to be applicable all the way up to the mass ratios reachable by numerical relativity late in the inspiral. And they also reach early enough in the inspiral to make contact to post-Newtonian theories. So we have this nice picture that post-Newtonian theory, small mass ratio approximation, and numerical relativity fills the diagram I was starting out with, the mass ratio frequency diagram of inspiraling binary black holes. Just to repeat, this is only for quasi-circular, this is only for non-spinning, and this is only happening at a phase error of about 1 radian. If you want tighter phase errors, then of course the region of validity of each of these methods shrinks. The small mass ratio becomes the dark red wedge here, and post-Newtonian recedes more to the top left, to earlier in the inspiral. And then again, you need fancy approximation techniques that are more accurate, like the UB methods or even higher post-Newtonian order. And also for eccentric systems, we expect post-Newtonian to be significantly worse. So again, it won't work. With that, I would like to summarize and entertain you with 2 more nice movies here. So the NR simulations are accurate enough for today's gravitational wave detectors and for the parameters of the gravitational wave event so far. A lot of improvements have happened and are happening to prepare for the future gravitational wave detectors, accuracy, length, parameter space coverage, high spins. I didn't talk much about the biggest challenges, high mass ratios and near extreme spins, thinking that Carlos Luster will do a lot of them. But I showed you promising results for eccentric inspirals and scattering encounters. And I would like you very much to thank you for your attention.
Thank you very much. So I think we have a few minutes for questions. Perhaps 1 or 2. Yeah, there are 2 questions. I'm not sure if they are ordered, but Aaron? Aaron? Okay, you have to unmute yourself and ask a question if you want. There's also a question by Thibault. I mean, there are hands up. I don't know if these are questions or simply hands up since a long time. Wait, let me see a chat. There's a problem with unmuting. Wait.
Can you hear me now?
Now, yes.
Perfect. Okay. Somehow it didn't work. Yeah, so thanks for the talk, Harald. I was interested in theories beyond GR and whether there are any simulations performed in theories beyond GR and whether you know of advantages, disadvantages compared to non-spectral codes.
So there's two primary difficulties with theories beyond GR. Number one, there's so many different ones, and every single one basically requires a lot of work whenever the principal operator of your equations change.
Yes.
And number two, a lot of these theories are not well-posed and do not have a well-posed initial value problem, which is required for numerical reliability.
But this is required for any code, right? So,
yes, that's required for any code, but it turns out to be particularly important for spectral methods because they tend to be a lot more finicky with actually getting everything perfectly right in the underlying formulation. Finite difference codes often still work somewhat, somehow, even if there's some mathematical problem in the formulation, the spectral method simply won't. Therefore, both in our collaboration and elsewhere, a lot of results are obtained only in linearization around GR. That typically leads to a few extra scalar fields that have to be evolved and then give you first order deviations from GR. In our collaboration, Leo Stein and Masha Okunakova are the primary people doing this work. And another important person in the community doing these simulations is Helvi Wittek, who is speaking later this week precisely about simulations beyond GR.
Thanks a lot.
Okay, Thibault, can you? Yes, no.
Thank you, Harald. Excellent talk. Just a short question. Do you intend to try to do ultra high energy scattering encounters?
I have forgotten to put down into the biggest challenges. High energy encounters. It turns out the high energy encounters are quite difficult to do, similarly to high spins and high mass ratios. All the current techniques become very inaccurate and the codes break down. Yes, it is on our to-do list, but we haven't really started in earnest. So my expectation is that initial speeds of the black holes like 0.2, 0.3, perhaps even 0.4 of the speed of light is no problem. But getting to 0.9, getting to 0.99 will be harder than getting to the commensurate number in spins. So I think it's actually easier to do a spin of 0.99 than to do a velocity of 0.99 interaction.
Okay, thank you.
Isn't there some simulation by Ulrich Sperache about the high energy encounters?
Yes, Uli and Franz did some simulations many a year ago. And they got up to a Lorentz factor of, I think, order unity. But the simulations were extremely difficult. The two primary difficulties are that the black holes by Lorentz contractions turn into pancakes, and that the chunk radiation, these initial gravitational wave transients I was showing you earlier, they move with the speed of light, and the black holes move essentially with the speed of light. So it's extremely difficult to reach the situation where the black holes encounter while the chunk radiation already has propagated away and doesn't mess up the problem.
Yeah. There is another question from David.
Thank you for a very engaging talk. I'm assuming, or perhaps this is naive, that it's straightforward for you to extract waveforms from the scattering of black holes.
Yes, we can extract waveforms from the scattering. And Hannes already sent me some to put in my talk. I left them out because I knew I had already too much to talk about, and I wasn't quite sure whether they are sufficiently correct and we understand them well enough yet. So the goal is to also extract gravitational waves. It's more difficult to do so because the black holes very quickly reach quite a significant distance from each other again. This introduces dipole moments into the background space-time that interact with the gravitational wave extraction. And also gravitational wave memory is much more important here than in other cases. And I think all of this can be taken into account, but given the time constraint, I didn't feel confident enough to show the waveforms we currently have.
I think this will be of interest to some of the amplitudes people who are doing the basically scattering, at the moment, mostly doing scattering domain calculations. I think that'll be an interesting opportunity to do some comparisons directly with numerical results.
So the amplitude calculations also result in the waveforms that are being emitted?
Well, I apologize for giving a preview, but you'll start to see an example of that tomorrow. I mean, this is very early stages still, but I think in the next year or two, we'll start to see more serious results that may be worthy of numerical comparisons.
Okay, that would be really exciting to do such comparisons. And especially the very first one, even if the results aren't particularly good yet on either side, typically these very first comparisons are still very telling and will teach both sides a lot about how to continue and improve their calculations.
Okay. There is a minute for a very last question. Otherwise, we have already covered 1 hour, which I think is beyond the time. So if someone wants to... No, it's fine. I think we also started a bit late. So, but if someone wants to ask a quick question, now it's the last chance. There's something in the chat. Okay, time's is over. I guess Harald will be available via email or during the break of the conference anyway to talk to people. So there will be other chances. So thank you again, Harald, and yeah. So
thank you very much for having me.
And I don't know who's next actually. Who has to chair? I certainly has to log out in short time. Prepare dinner.
I believe I'm next.
To chair or to talk?
Talk.
I'll think of a talk.
The Bern is the next to talk.
Yes.
So.
Okay, then Alessandro, will you take over?
I'm afraid I will have, because you have to leave, and we would have liked to have somebody else to chair, but unfortunately the organization was a bit fluid, so we have to improvise as usual. So next talk will be of Bern, who will talk about gravitational two-body Hamiltonians from scattering amplitudes. So please, Zvi, you have 45 minutes, and you can decide if you want to speak 30 minutes, 35, and leave 10 minutes for questions, or as you like.
Well, thank you. Okay, so I'll be explaining about some of the recent work that we've done on using scattering amplitudes for the two-body problem for gravitational waves. So this is work that we did in a number of papers. So the first paper that was with Clifford Chung, Radu Roiban, Xiaoxian Shen, Mikhail Solon, Mao Zhang, and then also we have there's Andres Luna, there's Julio Parra Martinez, Eric Sawyer, and then Michelle Roof joined us. Of course, as we all know, something very exciting happened, and we in the scattering amplitudes community were very eager to contribute to the problems of importance for gravitational wave physics. And here I'm going to give you an overview of some of our progress. And some of this will be touched on in some talks or entirely devoted in some other ones like Hassauer's talk. So I understand that there are people in the audience who are not experts, so I'm going to start with some kind of an overview of some of the ideas we use, and then I'll talk about some of the latest results. So the first thing will be just the outline of the problem, some basic ideas from scattering amplitudes, and some comments about useful structures that we make use of. The EFT approach, we use EFT matching to extract the physics that we want. And then I'll talk about the applications, the state-of-the-art two-body Hamiltonians. There's a new result that I'll explain a little bit about, which is order G to the fourth in the post-Minkowskian approximation. It's the conservative potential contributions that I'll present. And then a few other things like Connell formula for spinning case and results on tidal operators, and then I'll finish up with outlook. So the first thing that might be a little mysterious if you haven't seen this before is what do scattering amplitudes have to do with the classical dynamics of astrophysical objects? It looks quite different. In the case of the scattering amplitudes, we're thinking maybe about particle physics, and beams of particles come in. We use quantum field theory, and then particles come out. Use gauge theory, for example, QCD, electroweak theory. And that does not look at all like the case of gravitational waves, where you have a bounded orbit, and you're talking classical physics, you're talking about large objects, and general relativity. It doesn't look at all to be the same. But there's some important insight, a very simple idea, which is that the radiation we're interested in, its long wavelength, and therefore these black holes are point particles as far as we're concerned. Once they're point particles, then we can work with them. Then the ideas become applicable. This was understood earlier, but really systematized by Goldberger and Rothstein, this basic idea. Okay. And just to be clear, the part that we'll be talking about is the inspiral part. And we're going to be talking about it in what's called the post-Minkowskian approximation. It's an expansion in Newton's constant. Okay, and I don't think I have to explain exactly why we're doing this. That was covered very nicely in other talks. Just to explain the direction that we're heading, this I took from Alessandra Buonanno's talk in Amplitudes 2018, where she came and she explained what needs to be done. And there was this very nice table that explains how we're organizing things. There's the post-Newtonian approximation that we all know and love. It's the expansion in both V square and G. That's based on the idea of the virial theorem in the bound orbit case. And that's going down these columns. So the 0 PN, that's Newton. The 1 PN, that's the first correction, and so on and so forth. And then what the rows are is what's called the post-Minkowskian approximation, or we in particle theory, we just call it perturbation theory. It's just expanding in Newton's constant. And the idea is that we go across these columns, where we pick a row and go across the columns, where we work at a given order in G and all orders in velocity. So we maintain the Lorentz invariance. And this is completely natural from the point of view of particle physics, where we anyway are going to work in a relativistic framework. And Alessandra explained very nicely what needs to be done. There it is. That's what we needed to do. Maybe let me make a few comments about these amplitudes methods, these on-shell methods. It seems a little funny that we would approach the problem using a technique that seems to be quite distant from the problem at hand, which is the bound state orbital mechanics in general relativity. But a few comments of why we thought this would be a good idea. First thing is there's a long track record of these methods pushing the state of the art. There's in collider physics, there's something called the next to leading order QCD revolution, and that's doing very complicated processes. So this would be W plus 3, 4, 5 jets. This would be the diagram associated with a W plus 5 jets at next to leading order. These are the types of things that ordinary techniques, like the Feynman diagram techniques, even to this day, they haven't been able to do things like this. And then another example closer to gravity would be very high loop orders in supergravity, 5 loops in n equals 8 supergravity. So we understand that these types of methods are quite good for getting to high orders of perturbation theory. And one of the characteristics that I'll keep on emphasizing throughout the talk is that it's a gauge invariant formalism. We have asymptotic states, and then the choice of coordinates or the choice of gauge is not relevant as long as you have these asymptotic particles coming in from infinity. And another characteristic is uncovering useful structures. And that has to do directly tied to the fact it's a gauge invariant formalism. And one of the ideas that you'll see throughout the talk, is gravity is a sense gauge theory squared. We call it the double copy. And there's a number of other ideas, but this is the one that I'll emphasize here. And it also has a certain built-in efficiency in the way it works, is that you recycle information, that you take gravity integrams, the integrams that are associated with these diagrams, you build them from gauge theory, and it also meshes very well with integration methods. And this is something that it's going to become much more important as we go on to higher orders, because the integration is currently the most difficult step, you could say the bottleneck, but in fact we haven't even used the full power of the integration methods when they're combined with the unitarity methods, these on-shell methods. And by on-shell methods, what I'm referring to is just that you use Einstein's relation between the energy and momentum, and you should use that in intermediate steps. Normally, this is not the way you would do a calculation in particle physics with Feynman diagrams. You would take things off shell, but there's a whole systematic framework of how we're supposed to construct the entire amplitude to any order of perturbation theory by using only on-shell data. And there's a notion which we call generalized unitarity, where you take the normal ideas of, let's say, a 2-particle cut, a 3-particle cut, and you generalize it to objects like this, where these intermediate states, they're all on shell. In fact, you'll see these diagrams again when we talk about the gravitational problem, trying to figure out the two-body dynamics. Okay. Now, as an example, which I pretty much use in every talk, of what this helps us, or a way that this helps us, is a comparison of looking at gauge theory compared to the case of gravitons. Now, if you work in the normal gauges, this would be Feynman gauge. This is just the Donder gauge, and you do a comparison of these two vertices, the 3-gluon interaction and the 3-graviton interaction. You don't see much similarity between these two expressions. The graviton one is clearly much more complicated. In fact, it's much more complicated than it seems, because you have to put in some permutations here, and there's some symmetrization you have to do. And what you would conclude is that a problem in gravity is a much more complicated problem than that of gauge theory, especially as you go to higher orders of perturbation theory. But that is not correct. You should in fact look at the problem the on-shell way. You need to think about on-shell states on these interactions. And in fact, when you do that, you find something very remarkable. which is that the interaction of three gravitons looks like two copies, like a square, of the Yang-Mills interaction once you toss away this color factor. And you could just summarize it. Gravitons are like two gluons. Now, you might say, okay, this is very nice, but you're talking just 3 points. What you want is all orders of perturbation theory. Well, back in 1985, that was the first place this was understood, was these relations between gravity tree amplitudes and the gauge theory tree amplitudes, that they were just simply related sums of products of gauge theory give you gravity amplitudes. And by gravity, I mean gravity. I don't mean some exotic theory. You can think of this as a low energy limit of string theory. It was derived in string theory, but it holds in field theory, and it holds very generally. So we can have this mantra: gravity is like the product or the square of gauge theory. And this is this idea of recycling, that if you're interested in simplifying a gravity scattering amplitude, what you do is you simplify the gauge theory one, and then you feed it into these formulas, and out come simplified gravity expressions. And something that I think is quite remarkable about these formulas is, even to this day, and we've understood this now for quite a while, if you look at the Lagrangian methods, the ordinary Lagrangian or Hamiltonian methods, there's no hint of why this is actually true. But the key is that it has to be for on-shell states. You have to have an idea that it's quantities that are gauge independent. If they're gauge dependent, it becomes very hard to see this. There's another way of looking at it, and this is in fact the way that we use for the order g to the fourth for some technical reasons having to do with dimensional regularization. But in any case, there's another way, which is this, what we call the duality between color and kinematics. And that, what that is you take a gauge theory amplitude and you rewrite it. You rewrite the gauge theory amplitude as in terms of these cubic diagrams, where there's color factors, this kinematic numerator. The kinematic numerator depends on polarization and momenta, and then there's a set of propagators. And then what you do is you look at these cubic diagrams and you find triplets of them that satisfy the Jacobi identity. And the claim is that we can arrange numerators to have exactly this property and one-to-one correspondence. And you say, okay, that's very cute. What are you going to do with it? Well, the answer is right here. Once you've done this, once you've made this arrangement that the kinematic numerators and the color factors satisfy the same identities, then the magic is, if we want to go from a gauge theory amplitude to a Einstein gravity amplitude, we just take the color factor, replace it with a kinematic numerator. It's that simple. Okay, and this idea is we're going to use in the calculation. And by now there's quite a lot of work, which is too much for me to review in this time, on the a link between scattering amplitude methods and the binary black hole merger problem. But of course, the key question is, can you do something state of the art? Can you push the state of the art? After all, if you can't do that, then what exactly is the point of having some kind of new method? Well, the way we approach this problem is we combine the ideas from the amplitudes community and ideas from the EFT community. It's all explained in this paper, a very beautiful paper, Chung, Rothstein, Solon, that tells us how to do this. So we take all the ideas from here, from gravitational scattering, like the ones I just showed you. We use basic ideas of effective field theory, and we combine these two to give us post-Minkowskian potentials and Hamiltonians. Once we have the Hamiltonian, we can solve any problem, including or especially the bound state problem. So in a sense, what this machinery is about is to take the scattering data and convert it into data that is immediately useful and without any subtlety. It's just an ordinary Hamiltonian that one would use for the two-body problem. And I have to say there are nice ways of doing it that bypass this. However, whenever we go into new territory, whatever it might be, like, for example, you'll hear about a little bit about the tail effect, then we definitely prefer this way of doing things because of the clarity that it offers. And it's very clean from our point of view. This is well understood by our friends in the effective field theory community. We use this effective field theory to define the potential. If we're interested in black hole interaction, then we have fields A and B, which represent the black holes. There's an interaction between them. That's exactly the potential. And this is used to define the potential by matching to the full theory. Okay, and in that way, subtleties are taken care of. And the basic way this is done is you do on one side the full general relativity calculation. Now we're using quantum amplitude, so you need to take h bar goes to 0 quickly, so that you don't carry around too much excess baggage. And we use the methods, the heavy artillery. We take the double copy. We take the generalized unitarity. We take loop integration methods. We have a machinery that I'll describe a little bit for dealing with the loop integrals. And then at the end, we have a general relativity loop amplitude. Then we do a much simpler calculation in effective field theory, where we build an ansatz. We construct the effective field theory by an ansatz for the potential, feed it through Feynman diagrams. You don't need anything fancy. You integrate it, and then what we do is we match these two. We demand that these be identical. By demanding that it's identical, that determines what the coefficients in this ansatz for the potential is. And that determines the potential. We have the potential. We then have the Hamiltonian. We're good to go. Okay, and when we started looking at this problem, we realized that we were in unitarity heaven, because the problem, this bound state problem, fit perfectly into the tools that we have, the idea of unitarity and putting things on shell. There's two reasons for this. One is the long range forces. That means that the matter lines must be separated by propagators. So that effectively, the net effect is that we can consider these to be on shell. And then another simple rule, this is for what's called potential modes, is that there has to be one cut matter line per loop. So there has to be an on-shell leg as well. So that means that the ideas of unitarity, where we cut legs, fits perfectly into what we want. And for example, here at the order G cubed, then there's 3 unitarity cuts that we have to calculate. And just one example of how this is done is would be let's say this would be at the 1 loop. So this would be at order G square. So we have on-shell legs here. That means that these are 3-point amplitude. This is a 3-point amplitude. Here's a 3-point amplitude, 3-point amplitude, 4-point amplitude. So we take the product of a 3, 3, and 4-point amplitude that represents this cut. We sum over the intermediate states. And if in the double copy, you can get unwanted states, but I mean, just don't sum over them. Just project them out. That's quite simple. And then the gravity tree amplitudes are then rewritten in terms of products of gauge theory amplitudes. And you can see here's the input that we would use for this order G square. This would be a tree amplitude. There's the mass of the scalars. So this is spinless particles. And these 2 tree amplitudes would then be the input for this calculation. Okay, and by the way, if personally, I find it very amazing that you can consider the case of gravity by thinking about gauge theory. The theory of gravity clearly is not as far away from gauge theory as one might have thought. And this makes it very explicit that we literally put in gauge theory in order to calculate gravity. Okay. And just to jump to the answer. So there's some commotion about doing integrals. How you're supposed to organize it, and how you keep only the potential parts, and so forth. But anyway, here's the answer at order g cubed. So this would be a new state-of-the-art calculation when this was done. So this is our amplitude. So right now, this is at this point, it's not useful for the classical dynamics directly because it's a scattering amplitude. It contains, there's some pieces in here, that's F1 and F2. They don't have to be calculated because they're iterations of lower order pieces that we already know, so that they're not interesting. They're also infrared singular. So this part we don't need. And what's one thing that's quite remarkable about this expression is that it's quite compact. It also has this, there's an arc cinch here, and that's related, that gives us a mass singularity. And that mass singularity, there's actually quite a bit of discussion on it, but at the end, it's nothing too surprising. It cancels an identical mass singularity. If you were to include real radiation, we're doing conservative classical potential here. So there's radiation is not included, and then mass singularities can develop. And they, of course, cancel by general theorems. This is the Kinoshita-Lee-Naumburg theorem. Another thing that's actually quite interesting is these finite pieces that are here. You can directly connect them to the scattering angle, and that was in our paper and expanded on by Callan Porto and then also the Niels Bohr group. Something else that's actually pretty interesting that's in here is if you study the mass dependence of this, that was observed in the paper Unano's group, and then a very comprehensive understanding of that is given by Damour for organizing the mass dependence and connecting it to the cell force. Okay, here's the Hamiltonian. So this is now directly useful in the problem of the two-body interactions, the conservative two-body interactions. It's not so bad. It's relatively simple in terms of some standard variables. And if you want to understand exactly what this is, you can just series expand it in velocity, and then that would match on to corresponding terms in the post-Newtonian approximation. And an important question is, how do we know it's right? There's a lot of strange things, at least if you're not coming from the amplitudes community. Certainly looks very strange in how we approach this problem. So you want to know if this is correct. And of course, the first thing we did is we compared to the literature, to the 4PN Hamiltonians. You have to do a canonical transformation because while I was stressing that our formalism is gauge invariant, at the very end, when you go to a potential or to a Hamiltonian, that is not a gauge invariant quantity. It's just a generator of the equations of motion. Finally, you have to do canonical transformation, and it agreed. Thibault, he seriously questioned the correctness of our work, and in fact, he had a specific proposal on how to correct our expressions. If you're interested in what that commotion was about, you can look at Thibault's paper, the version 1. But in any case, since that time, there have been multiple subsequent calculations, and they all confirm that we have done it correctly. There's papers from Blumlein, Bini, Damour, GReCO, where they look at the 6PN overlap. So this is really quite good. So now I think our work has withstood some careful scrutiny, which is quite nice. And there's also other checks. There's subsequent calculations that reproduce the 3 p.m. result. There's scattering angle checks. There's also an understanding of this issue of the real radiation and the mass singularity that was nicely understood. Aki Damour very cleanly cleaned all of that up. Okay, what about the next order? Just this year, we calculated the potential mode contributions. That's order G to the 4th contributions. Now, a lot of this is fairly straightforward compared to what we did at the previous order. And of course, by the way, this calculation is not only important for just wanting to go on in orders of perturbation theory and the phenomenology of it, but it's also to understand about the scaling of the methods. So if the methods scale well, there's a way of testing it. You should just go on to the next order. That's the argument that the methods scale well. So that's another reason we're very keen on doing this. The integrands are quite straightforward. There's 8 unitarity cuts instead of 3. You have 6-point trees instead of 5, but the basic methodology is identical. But there's some new features. Well, the first thing is because of the way the integrals are organized and the fact that they're more complicated, we wanted to use dimensional regularization, and that required some reorganization exactly how we do things. And we found a very nice reorganization in terms of the radial action. So if we look at the one loop amplitude, the first order, if you look at the first order of perturbation theory, so that would be the tree, then this is the radial action. It's just an observation. But if you organize things just the right way, then what happens is that the next order is given by, again, a contribution to the radial action, and then terms that are just iterations. And this requires a specific choice of how the iterations are defined, because you can toss terms back and forth between here. And different ways of doing that have different advantages. In our last paper at the order G cubed, we organized it in a different way, which had its own reasons why that was a good way of doing it. But here, at this order, we found it very convenient to organize things in a particular way of defining what these iteration terms are. And it's quite clean in how it works out. Essentially, the answer of what is this scattering amplitude is that it's just essentially, you could think of it as an exponentiation of the radial action. And this radial action is directly connected to the scattering angle. So there's a very simple relationship which we uncovered in doing this, and it helps us calculate, because once we've organized things in just this way, then these iteration terms are not interesting. They just cancel immediately against the effective field theory, and they don't even have to be calculated, although of course we calculated those pieces. Now the integration, that's a serious issue that you have to really deal with very effectively. In the amplitudes world, we have a lot of experience with that. That comes from collider physics. That in collider physics, there's a whole set of machinery that we make use of in order to do integrals. And that is what we import. So the way we set this thing up is with a hybrid approach. We use the non-relativistic integration that we used in the order G cubed, and that's basically doing it by taking the integrals and doing a velocity expansion and then trying to resum. But here we don't bother with the resummation. We just use it for boundary conditions that we then feed into the next step, which is to use the machinery of QCD, which is integration by parts, differential equations. And one of the key points, this is a beautiful paper from Julio, Michel, and Mao. And what they observe is that the integrals, to all orders of perturbation theory, they're single scale integrals. And once they're single scale integrals, these methods really shine, because these methods were developed for much more complicated problems in QCD. Once you have single scale integrals, then you can really go forward. And the basic idea that this is based on is integration by parts. That requires the dimensional regularization so that these integrals converge properly. And you just write down a total derivative, expand it out, that gives you linear relations between integrals, and then you systematically solve the system in terms of master integrals. And then the differential equations comes hand in glove with this method. You take a derivative of a master integral with respect to some kinematic invariant, you get some mess, you feed it through the integration by parts, put it back into master integrals, then you have a system of equations that you have to solve. And the solution of the differential equations, it's generally not so hard. If you know what the basis of functions are, if you don't know what the basis of functions are, then you can series expand to extremely high orders. A series expand, for example, in the velocity. Now there's, at the order that we're working, we use just straightforward tools, nothing fancy. We use Fire 6 off the shelf, more than sufficient for this problem. And another little issue is elliptic integrals. They make their appearance. For a while they were more annoying, but when all the dust settles, they're actually just a minor annoyance in dealing with this. And I should mention, we haven't even used the full power of these methods. At the order we're working, just off-the-shelf software that you download off the internet works quite well. But at higher orders, we're going to have to use modified versions that make use of the unitarity conditions. Okay, and here's the answer. So this would be the order G to the fourth contribution to the amplitude. And it comes with certain pieces we've organized a certain way. There would be a piece that we could just call the test particle. It's right here. This piece could have been predicted without any trouble. Then there's what we would call the first cell force contribution. There's a tail effect. The tail effect, you notice there's a singularity here, 1 over epsilon, that's dimensional regularization. The reason why our answer is infrared singular is because this is only the potential modes. We have not included radiation effects. Once we include the radiation effects, there will be no infrared singularity here, but there will be some extra pieces that we haven't included. Then there's a whole bunch of iteration terms. They're not so interesting because they just automatically cancel against the effective field theory, and they don't affect the physics, or we've already accounted for these iteration terms. And the answer, you can see, is written out here in terms of some coefficients. They're given in the table. Okay, it's much more complicated than the order G cubed, but of course, well, it is one more order, so you shouldn't be too surprised that it gets more complicated. There's some interesting structures in here if you look more carefully. And you'll see here's our friends, the elliptic integrals. Elliptic integrals are our friends now. Mathematica knows these elliptic integrals, therefore no issue whatsoever. And the radial action, we can read it off directly from here. It's just a Fourier transform. You just have to Fourier transform, and you'll see exactly this expression. Oops, you'll see this right here. This matches what you see here. There's a Fourier transform caught in here that changes some numbers, but anyway, it's basically just read off from here after Fourier transform. And just to emphasize, this thing is incomplete right now because we're missing the radiation contributions, non-local and time effects to the tail effect. Once we include that, then there'll be no infrared singularity there. And of course, we're working on this. I don't have anything to report about that today. And maybe one cute little thing is that this thing does have a mass singularity. It's actually a kind of nasty one. It goes like 1 over m. At order g cubed, that was a log singularity. Here it's a power singularity. Presumably that will cancel against real radiation, just as it did in the previous order. Okay, here's the Hamiltonian. So this would be the thing that you could feed into two-particle dynamics. As I said, it's still incomplete because there's an infrared singularity there. Actually, something very nice is that this infrared singularity is connected to the energy radiated. That was understood bini Damore and GReCO. There's a direct calculation which we match. That would be Hermann, Martinez, Ruf, and Zhang. They also calculated other quantities like radiated momentum. There's also been, since our work, there's also been some subsequent calculations, and we have agreement to end the overlap through 6 p.m. So I think it's likely this is correct. Oh, here's something very cute. So we already saw this in Bonanno's talk. Okay, so there's some pieces missing, so you shouldn't take this as being conclusive of anything, but still, it's a very nice plot, shows us that we're on the right track, which is the binding energy and cycles. This is cycles before the merger. And what happens is if you look at lower orders, let's say for the Hamiltonian, the third post-Minkowski Hamiltonian, it starts not doing very well towards the end compared to the professional grade comparison, numerical relativity and the effect of one body. But if you just look at this 4 p.m., but we're going to drop a piece, that piece has to cancel, but there are also finite pieces which were not included after that cancellation. What you find is that it's actually remarkably good, shockingly good, I would say. And of course, this is not conclusive because it's done with incomplete calculation. But it certainly motivates us to finish non-local radiation tail contributions. I don't think we need more motivation than that. Let me just show you a few more things. Iconal phase insight. So the iconal phase is something very natural from thinking about classical limits and scattering amplitudes. I think it'll be a nice talk from Rousseau, who's going to explain more about that. And the idea is that you can write the amplitude in a form where you can use stationary phase approximation, and then from that you can get things like the momentum kick in terms of a derivative on a phase. This iconal phase idea is that it controls the dynamics of the scattering. And you don't have to solve Hamilton's equation. You just work out this, read off the phase, and then take a derivative, and then you're done. And we expect this to be very general. The question is how general? So we had a look at this, for example, in a complicated problem, which is spin. Spin seems like a good case because it's not completely obvious that there would be an iconal phase, but in any case, you can guess that there should be something like that. And we looked at the case of spins non-aligned. Orbital angular momentum is not conserved. The orbital motion is complicated. It's not in a plane. And the question is there a scalar function called the iconal phase that then controls the dynamics? You can check that this is true pretty straightforwardly at the lowest order. So in terms of Feynman diagrams, it'd be this Feynman diagram. And there's a phase that you can get in terms of, there's a spin. And these coefficients, you can find these coefficients in our paper. And sure enough, you can check that if you solve Hamilton's equation, and work out what the impulse and spin kick are, then in fact it is given exactly by this iconal phase by taking appropriate derivatives or Poisson brackets. And this was observed also earlier. It was observed earlier using a somewhat different setup with covariant spin. We use body-centered spin. Now, how general is this? Well, we have a conjecture. We think there's a formula that says that the spin kick or the impulse or some observable is given by this expression in terms of the iconal phase at any order. Okay, we don't know if this is actually true, but we've checked this the good old-fashioned way by doing calculations of order G square, spin 1, spin 2, also a recent calculation, spin square, that's from Cosmopolis and Luna. And indeed, this thing works with no subtlety. Okay, and one comment is these are observables for scattering, but in fact, I'm sure that Rafael Porto is going to talk about analytic continuations of scattering observables to bound state observables. And there's probably the similar formulas that are there for covariant instead of rest frame spin. And this is just an example of the type of insight that you can get from the from scattering amplitudes. Maybe one more, and I see I'm almost out of time. One more would be that's kind of neat is this double copy. So this would be double copy for spin. So let's consider the energy momentum tensor at order G, arbitrary spin. So this would match onto the Kerr black hole if we took these coefficients. There's a set of coefficients here. I take these coefficients to be equal to 1, and then that would then match what Vines had for the energy momentum tensor. And you can ask, can you factorize this thing with arbitrary spin into a gauge theory? And the answer is yes. You can check this explicitly. It's in our paper. That there's literally a factorization, a double copy factorization, which is actually kind of remarkable that it's that simple. That the energy momentum tensor of gravity and the energy momentum tensor of what's essentially electromagnetism, that they're related in this simple way. One thing is this only works on shell. If you take these off shell, you work in some particular gauge, this is just not going to be true. I see I'm out of time. Let me just say that these same types of ideas that can be applied to tidal effects using a set of operators. Those operators, they can be mapped, at least at leading order, to world line operators, which is the more popular way of doing things. And you can do all sorts of cool things like work out potentials for infinite sequences of operators in terms of some closed form formulas that unfortunately I'm out of time that I won't explain, but in any case, you can do these infinite sequences, which is very cool. Okay, so what's the outlook? Well, the amplitudes methods, they have a lot of promise, and their use has been tested in a variety of problems. Probably the most important one is pushing the state of the art. Pushing the state of the art for high orders in Newton's constant, problems in radiation. There's already been quite a bit of work on that, and more coming. Finite size effects, spin effects. And one comment is much of the future progress is going to be driven by our ability to evaluate integrals. I think that the on-shell versions of the integration by parts method are going to certainly get us to the next order. And then once we're there, we're going to have a look around to see how things might work at orders beyond that. So the summary is that amplitudes provide a new and useful way to think about problems of direct interest to the gravitational wave community. amplitudes are independent of gauges, coordinates, and field variables, making it simple to identify useful new structures. The double copy was one that we find very useful and interesting. The methods, they've been tested in a variety of problems, and examples are pushing high orders of perturbation theory, so there'd be order G to the fourth. We have the potential mode contributions complete and published, the radiation contributions to the tail of their progress. I showed you just a little bit about the iconal encoding of spin observables and all order conjecture. There's explicit results for infinite sequences of tidal operators. And then some kind of neat thing about the energy momentum tensor having a simple double copy. And I think the most exciting part is that the methods, including those for integration, they're not close to exhausted. I think much more is going to come. And in the coming years, we can expect new advances, not only for the gravitational wave physics, but also for understanding gravity and its relation to gauge theory. Okay, thank you.
Thank you very much. Very nice talk. Any questions? I think we can take 3 questions. Gabriele, can you unmute yourself?
Yeah.
Yes.
Yeah. Okay. Thank you, Svi, for the very nice talk. Just one thing I would like to understand, maybe not today, maybe in the coming weeks, is the relation you were alluding to Kinoshita's theorem. Because, okay, it looks to me that the cancellation of the mass divergence here, it's on a different ground than the usual cancellation of infrared divergences, which, you know, refers to cross sections, you know, exclusive cross section being infrared singular, but if you add inelastic Bremsstrahlung channels, you remove the divergence. Here, it seems to be a cancellation within the elastic amplitude, the real part of the elastic amplitude, which provides the phase shift or the iconal, the real part of the iconal, and therefore removes the singularity in the scattering angle. And also, you see, Kinoshita, Lee-Nauenberg was really first formulated for gauge theories, okay, of QED in particular, where there are mass singularities, whereas in gravity, it's supposed to be no mass singularities. Right. So, okay, I think...
So the way, yeah, those are all, of course, very good points.
But I don't see...
Okay, so the first thing, if you look at the Lee-Nauenberg theorem, it's remarkably, I don't know what the right word is, vague, that in the sense, well, the key point is that the way I interpret that theorem is if you're looking at a physical observable, never mind the details of how you got it, right? So like you point out, normally it's phrased in terms of thinking about cross sections, never mind cross sections, physical observables, okay? Now, so immediately the expectation is that for physical observables, infrared cancellations will, infrared singularities will cancel, right? So in a sense, that's, you could say that's you could say the heart of what that little comment was, right? And I think you will agree that this must be true, and it's tied to the Lee-Nauenberg thing. The other point is in gravity. The way it works, if you look in detail, is the mass singularities cancel in non-trivial ways between different pieces. Mm-hmm. Right. So gravity is different from the case of gauge theory in the sense that in gauge theory, the mass singularities do not cancel within, let's say, virtual alone. Right? They have to cancel against real radiation in a non-trivial way. In gravity, the way it works is it cancels within virtual by itself. Yeah. But if you look at how that actually works, it's a cancellation between different sets of diagrams. And what happens in the classical limit is that some of those diagrams get pushed off into H bar, higher order in H bar. Nevertheless, you could say, or nevertheless, the way I see it in gravity, there's a double cancellation. There's a cancellation within the virtual, and then on top of it, the ideas of the Lee-Naumburg theorem, they're still active.
Of course. There are
So
many
what's
cases
happening,
of divergence.
the way this mass singularity appears is one of the two cancellations disappeared. So in gravity, you could say we're doubly protected against mass singularities. One is they cancel among themselves within the let's say within the sub pieces like the virtual, and also separately in the real. But then on top of it, even if they wouldn't cancel that this way, the way they normally cancel in gravity, they anyway cancel once you go to a physical observable. So it's just a comment, you could say, on the expectation from the very beginning. Certainly I was thinking, oh, whatever's going on here, it must have something to do with real radiation. And presumably you were thinking exactly the same thing in your work. And presumably in the back of your mind you're thinking about, oh, these things can't be physical. And where did you get that from? Presumably from the Lee-Naumburg theorem.
Okay, thank you.
Yeah.
Luc.
Oh, hello, nice talk. Thank you very much. I have a question on the radiation tail term in the 4 p.m. Hamiltonian. So you expect that the poles that you have will be cancelled, which come from the potential mode, will be cancelled by this term. But what is crucial is the term beyond the pole, the finite part. And my question is, in which form do you expect to get it? Will it be a closed form, analytic closed form expression for some non-local integral, or will it be in closed form only if you re-expand it in a post-Newtonian way, and then in principle you should recover in the post-Newtonian approximation part of the 4 p.m. term, tail term, which at 4 p.m. order is made, I think, of powers G4 and also G5. So,
well, that question is very hard to answer without having the explicit expression. For example, if you look at, you could have asked the same question, let's say a week before we had finished this calculation, the one that's on the screen. Are you going to get a closed form expression in terms of elliptic integrals? Are there elliptic integrals, and so forth? What's the details of the analytic form of the expression? And let's say a couple of weeks before we finished, that would have been very difficult to answer, because it's very, you could say there's some luck involved. Let's say this idea, can you get a closed form expression? There's a little bit of luck involved in that, because it depends what functions we would have found here, right? What are the precise elliptic integrals? They happen to have been just normal, commonly found elliptic integrals that are you could say well defined in Mathematica. So therefore we have a nice closed form expression. However, let's suppose in this case that we did not have a closed form expression. It just turned out that for whatever reason the elliptic integrals were some unknown integrals that are not standard in some way, so then what we would have done is we would have done a velocity expansion, maybe to 1,000 orders. In our paper we say 400 orders, but let's say if we needed it, we could do, let's say, 1,000 orders in velocity. And that we would then use to define a function in some ways, through some kind of interpolation to define a function. So I don't know, it's much better if we find a closed form expression. However, I don't think that stops us. It's not as nice if we had some kind of, let's say, very, very high order velocity expansion, for practical use. I'm not sure if that would make much difference. although we are definitely going to work hard to give you a closed form, compact expression for those tail terms. But I can't say more right now about it until we're complete.
We'll re-expand it in a post-Newtonian way and check with the literature.
Yeah, well, of course, everything, we're very grateful to our post-Newtonian friends who have given us the, the velocity expansion. That is absolutely crucial for us to make sure that we've done it correctly. And indeed, you could say we're completely compatible with that in the sense that when we do a velocity expansion, then we, by definition, the way we work, that has to be identical to what you would find in the post-Newtonian way.
Thank you.
Okay, thank you very much. Any more questions? Don't see. I don't see anything. So, Gabriele, it seems that we should close here. I didn't want to be the last one to close this today. This was improvised, but anyway, I want to thank you, Zvi, again.
Yeah, we should thank all the speakers, remind everybody again that tomorrow we start and finish half an hour earlier. Okay, but otherwise, I think we are pretty much on time for ending the session.
Pretty much.
Thank you for the improvised chairman. Okay, goodbye, everybody.
Everybody,
Tomorrow.
bye. Bye.
Bye-bye. And you can keep interacting on Slack, I think, if people want to continue discussing.
What?
Okay.
Yeah.
Bye.
Bye-bye.
More or less.